In this 3 days mega event, we are going to have 17 plenary talks from the eminent scientists of various facets of chemistry and material science. And we'll be having about 130 oral presentations in 7 different streams. I see this as a wonderful opportunity, especially for the young researchers, to interact with the experts of their research field, discuss the ideas, gain the knowledge. I hope all the participants would make a proper use of this digital form. With all your support, I'm sure we'll make this conference a grand success. So today, for this inaugural ceremony, we have the dignitaries of our institute with us, Professor Balakrishnan Shankar, Associate Dean, Amrita Vishwavidyapeetham, Amritapuri Campus, and Professor V.M. Nandakumaran, Principal, Amrita School of Arts and Science, Amritapuri, and Professor Mangalam R., Chairperson, Department of Chemistry. We'll begin the program with a prayer. I request Mr. Krishna Nodni to sing the prayer.
Gajananam Bhutaganaadisevitam Kapitthajambu Bhalasarabhakshiram Umasutam Shokavinashakaranam Namami Vikhneshwara Padapangajam Dhyayamo Dhavalavakundanavatim Tejomayim Naishtikim Snigdhapangavilokinim Bhagavatim Mandasmitashrimukhim Balsalyamritavarshinim Sumadhuram Sankirtanalapinim Shyamangim Madhusigdhasuktim Amritanandatmikam Ishwari.
Thank you, Krishna Nunni, for making this morning more blissful. Now, I request Professor Mangalam R. to welcome the gathering.
Am I audible?
Yes, ma'am, you can go.
Om Namah Shivaya. Warm greetings of the day. My humble pranams at the lotus feet of Amma, Mata Amritanandamayi Devi, our Chancellor, seeking her blessings for our first online international conference. Distinguished keynote speakers for the 3 days conference, Dr. Bala, our Dynamic Associate Dean, our dear Principal, Dr. Nandakumaran, my colleagues, students, and all others who may be attending from different parts of the country and globe. It is indeed a great pleasure to welcome all the 17 distinguished speakers for the 3 days conference who will be enriching our knowledge in their respective areas of research. We are extremely fortunate to have keynote address by 6 eminent professors today, each one expert in their respective fields. Professor Jingley from Rutgers University, New Jersey, US, will be speaking on highly luminescent hybrid phosphors for energy efficient lighting technology. Professor E.D. Jemis from IISc Bangalore will talk on benzene to borofene and everything in between. Dr. Radhakrishnan KV from National Institute for Interdisciplinary Science and Technology, Trivandrum, will be taking us through bioprospecting of medicinal plants used in herbal formulations. Professor Martin Sig from University of KwaZulu-Natal in Durban, South Africa, will be giving a talk on nanotechnology for wastewater treatment. Professor Sabu Thomas from MG University, Kottayam, Kerala, will present a talk on interfacial modification in nanocomposites to tailor functionalities. And Professor Suresh C. Pillai from Institute of Technology, Sligo, Ireland, will be delivering a talk on new insights into solar and visible light active photocatalysis. So we have 6 talks on diverse areas. A very warm welcome to all the speakers who have graciously consented to give keynote address for the conference amidst their busy schedule. A warm welcome to our Associate Dean, Dr. Bala, and our Principal, Dr. Nandakumaran, who have agreed to be a part of this inaugural function in spite of their other engagements at such early hours of the day. To all my committed colleagues, to all our dear students, and to all other participants from various parts of the globe for this inaugural function. Research in chemistry is advancing by leaps and bounds, and therefore it becomes important for us to keep abreast of the latest developments in the field. This is where a conference becomes imperative in our curriculum. Today, material science is the most active area of research involving physics, chemistry, and many engineering streams, making it truly interdisciplinary. Breakthroughs in this field are likely to affect the future of technology significantly. This conference will be a platform for researchers from various fields of science and engineering to come together and share their expertise and research. World over, we are all passing through a very difficult situation due to pandemic COVID-19. We have taken advantage of the current situation to conduct an online international conference, which would be extremely difficult to organize in normal conditions. Thanks to the advanced technology, we are able to have a great team from different parts of the world come together in a common platform, which would be challenging to conduct offline. This is the first conference from our department, and we hope to make this a regular feature hereafter. Such activities will be very beneficial for a larger section of students from all over the globe. Online activities are thus much more far-reaching. Let us now get on to the rest of the program. I once again extend a very warm welcome to one and all for the 3 days program International Conference on Advanced Material Science and Chemistry, conducted by Chemistry Department, Amrita School of Arts and Sciences, Kollam, Kerala. Dear chemistry students, stay tuned for all the talks. I'm sure we are all going to have a very enriching experience. Thank you, one and all.
Thank you very much, ma'am. Now I request Professor Balakrishnan Shankar to give opening remarks.
Good morning, Namaskar all. Am I audible?
Yes, sir. Yes, sir.
Okay. It's wonderful that the chemistry department has set up this international conference on advances in materials and chemistry here in the end. I congratulate the chemistry department. I congratulate all of you, all my colleagues here at the chemistry department and the Amrita School of Arts and Science for utilizing their COVID time so nicely and setting up this online international conference. I'm also very happy to see several guests from all over the world and delegates from all over the world participating in this conference. As Dr. Mangalam said, there are 6 keynote talks today from professors all over the world. Professor Jingli, Professor Jemes, Dr. Radhakrishnan, Professor Bais Martin C., Professor Sabu Thomas, and Professor Suresh Pillai from Rutgers and Ireland and IIST and NIST and from South Africa. And it's wonderful to see this international participation. Advances in materials is perhaps the most important thing in this world today. Um, from a mechanical engineering background, I will tell you that pretty much from the design point of view, from a structural point of view, for example, that analytical formulations are all already done. So the next step is to find materials that have completely new properties and that can, you know, be harvested for these new properties in the maximum possible way. For example, here in the fields of renewable energy, the fields of energy storage, in the field of communication, and even in the silicon chip, in the integrated chip that we use all over the world, advances in materials is what's making the next step. So, so once again, I congratulate the Department of Chemistry to having set up this wonderful conference. I invite all of you from all over the world to online to our conference here. If it had been any other time, you would have actually been visiting here and seen our beautiful campus. But in any case, I welcome all of you here and wish you all the best. And I wish this conference all the success. Thank you.
Thank you very much for your time and support, sir. I request Professor Nandakumaran to address the gathering.
Om Namah Shivaya. Can you hear me?
Yes, sir.
Distinguished scientists from all over the world, Dr. Bala, Dr. Mangalam, and other faculty members of the chemistry department, and dear participants. I'm extremely happy that the Department of Chemistry is organizing an online international conference on advances in material science and chemistry. It is commendable that they have organized this 3-day conference involving scientists from almost all parts of the world during this, especially during these stressful days of the pandemic. So basically, they have utilized the COVID days very, very effectively by organizing this conference. This conference, which is basically interdisciplinary in nature, covers a wide spectrum of subjects, as you can see from the brochure. We have discussions about energy efficient lighting, nanocomposites, porophenes, nanocarbons, biosensors, fuel cells, and many more. Many novel materials have been fabricated, and I am sure during these days, these things will be discussed thoroughly. These materials, apart from their applications, are fascinating in their own right. I thank all the speakers from all over the world who have agreed to participate in this conference. I understand there are some speakers for whom this is midnight. I especially thank them for being awake at this time of the day and participate in this conference. I must congratulate the faculty of members of the chemistry department for organizing such a wonderful conference in a relatively short period of time. Probably in future, this is going to be the format in which conferences will be organized, online formats. So even after the COVID days, probably this become very popular. But at least in my understanding, there'll be something that which lack in this kind of online conferences. That will be the one-to-one and the one-to-many interaction that people will have with the scientists in the that we have in the regular format, which in a way leads to good collaborations. That's probably the one thing that lacks. Maybe only the oldies like us will feel like that. The youngsters probably will catch on, and for them, online conference will be extremely useful and fruitful. I wish the conference all success and hope that the participants will have a good time during the next 3 days. Thank you. Thank you for your patience. Once again, thank you.
Thank you very much for your time and support, sir. Once again, I thank all the dignitaries of the Institute for giving their time and support, extending their support for this conference. Now, this is the time to move to the main event of today. We have Professor Jing Li as our first speaker. Professor Jing Li is from Rutgers University, New Jersey. I call upon Dr. Smita Chandran to introduce Professor Jing Li to the audience.
Namshivaya. Am I audible, sir? Am I audible, sir?
Yes, ma'am.
Namshivaya. It is my humble pranams at the lotus feet of our beloved Amma. Good morning to 100 present here. It is my pleasure to introduce Professor Jing Li, an internationally well-known chemist, distinguished professor, Department of Chemistry and Chemical Biology, Rutgers University, New Jersey. Her current research focused on designing and developing new materials for applications in the field of renewable and sustainable energy. She has her MS and PhD from Cornell University, and her PhD guide is Professor Hoffman, who was a well-known chemist and Nobel laureate. And she had several numerous publications in high-impact peer-reviewed journals. She is a recipient of several awards and honors. Some of them include highly cited researcher from Thomson Reuters, the Clean Energy Education and Empowerment Award from the US Department of Energy, Chen Kong Guest Chair Professor Award from Ministry of Education of China, Excellence Award Chinese American Society, Board of Trustees Award for Excellence in Research. We are very fortunate to have Professor Jing Li with us today. Today's topic of our presentation is highly luminescent hybrid phosphors for energy efficient lighting technology. Now over to you, Jing Li ma'am.
Thank you. Thank you very much for your introduction. Can you all hear me?
Yes, Professor Jing Li.
Hi, can you also see my slides?
Yes, yeah, it's
okay.
It's all set.
Wonderful. Good morning to all of you on the other side of the globe, and good evening to anyone who might be here on my side of the globe. It's my great pleasure to have this opportunity to talk to you about our recent progress in developing highly luminescent hybrid materials for possible use of the phosphors in energy efficient lighting technology. Now, as many of you probably know very well, solid state lighting is a relatively new lighting technology that makes use of semiconductor materials to convert electricity directly to light. Comparing to conventional lighting sources such as incandescent bulbs and fluorescent lamps, solid state lighting technology is much more energy efficient and longer lasting. As the numbers here speak, switching to SSL in the next 10 years or so will not only greatly reduce the electricity consumption and energy cost, but also decrease the carbon dioxide emission by a large percentage, directly contributing to the environmental protection. The two most rapidly growing branches of SSL are LEDs and OLEDs, which are based on inorganic and organic semiconductors respectively. White LEDs, obviously, are LEDs that produce white light. These systems are of highest demand because of their great need in general lighting and illumination applications. Currently, there are two major systems. The first one is multi-chip based white LEDs, where 3 single-chip LED, red, green, and blue, are combined to generate white light. This type of white LEDs have lots of good features with high color quality, but the main problem is the high cost. And it is for this reason that this system is not currently on the market. The second system is single-chip based or phosphor conversion white LED, which involves coating of a blue chip or a near UV or UV chip by a single or multiple or multi-component phosphors. So here are the two examples, blue chip and UV chip, yellow phosphor, multi-component phosphor. So YAG-CE is a benchmark yellow phosphor with very high performance. Okay, so it's an internal quantum yield or photoluminescence quantum yield. These two are equivalent. It's very high, 95%. And so this system is much more cost effective, and it is currently dominating the LED market. However, there is also a drawback, that is, all phosphors used in these LEDs are totally dependent on rare earth elements. As you know, IEEs are essential ingredients for almost all high techs, okay? And their need will continue to raise very rapidly in the days to come. So there is a real risk in both their supply and the cost. And also, in addition, the very negative impact of their mining process to the environment eventually will become a very serious threat. And so developing alternative phosphors that have little or no dependence on rare earth elements is very much needed. So motivated by such need, we have worked quite extensively over the past several years exploring high-performance hybrid phosphor materials that are totally free of IEEs. So far, we have developed 3 hybrid phosphor families. The first type is based on 2,6 semiconductor inorganic modules with alkyl amines. The second type is composed of copper halide inorganic modules with organic ligands that contain nitrogen. The third type are luminescent metal organic frameworks, or LMOFs. Now, because of the time limit today, I will be only focusing on 2 of these, type 2 and type 3, which represent our more recent work. Now, for type 2 hybrid phosphors, as I just mentioned, the inorganic modules are copper halide in form of either a molecular cluster, a one-dimensional chain, or 2-dimensional layers. X can be chlorine, bromine, and iodine, but the examples I will be presenting today will be all based on copper iodide. Okay, so the organic ligand here are nitrogen-containing ones that can be either aliphatic or aromatic. Now, our initial effort was to find a way to achieve different emission energy and emission color. In order to do that, we designed a series of compounds with very closely related structures. So all of them would contain the same inorganic modules indicated in the blue sheets here. And their organic ligand will differ by only a small functional group indicated as R here. This would allow us to fine-tune their optical properties in a fully controllable and systematic way. So let me show you a set of such combinations of inorganic module and organic ligands. So in this case, the inorganic module is a copper iodide as a staircase-like chain. Okay, the sign color in my presentation is for copper, and the purple color ball is for iodine. The organic ligands, in this case, would be a pyridine and pyridine derivatives. Okay, so at the bottom, I show you 5 representative structures that we have synthesized and structurally characterized. Of course, we have many more than these. But in any event, as you see, all of these structures contain the same one-dimensional chain of copper iodide, and their organic ligands are pyridine and the 4 derivatives from this chart. Now, our DFT calculations show that for this type of compounds, the valence bands are primarily composed of inorganic component, namely copper 3D and iodine 5P. But for the conduction bands, the main contributions are from organic atomic states, specifically carbon and nitrogen 2p orbitals that make up the normal orbital of the ligands. This information is very important because it would allow us to pre-select and pre-design ligands that have suitable functional groups to lead to desired normal energy levels, so that we can precisely tune or control the band gap of the resultant hybrid structures, and consequently their emission energy and emission color. As you see from this table, there is a full correlation between the normal energy energy levels of the 7 ligands that we chose with the emission energy and the emission color of the corresponding 7 hybrid structures shown here. And on the top, you see the actual photoluminescence spectra of these 7 hybrid structures, along with that of the parent inorganic compound or semiconductor copper iodide. So essentially, with this approach, we are able to achieve any color that we desire over the entire visible spectrum. So this finding is very encouraging, but there is a catch, as some of you may have noticed. Their quantum efficiencies, luminescence quantum efficiencies or quantum yields are not particularly high, with the best value only a little more than 1/3 of the Icamsc, the commercial benchmark yellow phosphor. So in order to improve their quantum efficiencies, we then carried out a careful screening study on many of these structures that are composed of different types of inorganic modules, such as molecular species or clusters and one-dimensional chains and two-dimensional layers. What we found is that those structures that are built of molecular species, such as rhombic dimer in this case and the cubic tetramer in this case, have a much better performance than those that are made of the extended networks, chains, or layers. On the next slide, I show you some examples of these molecular species. As you can see, their emission energies and colors are also tunable, and they have a very impressive photoluminescence quantum yields, more than 90%, very close to commercial phosphors. However, it is not surprising to see that they're not very stable due to the molecular nature. Their decomposition temperatures with 60 degrees Celsius or lower even under protective air, this is under nitrogen, make them out of consideration for any possible commercial use. So the question is, how can we keep these great properties but make these compounds more stable? Here we applied the two approaches. The first one is to take these molecular species as precursor and combine them with suitable ligands that have a multi-binding site to form extended network structures through self-assembly process. As you know, the network structures are almost always much more stable than the molecular species. And so we succeeded in doing this. Here again, I show you 5 structures that we have obtained. So these are either 2D networks or 3-dimensional networks. In all cases, the molecular identity, whether it is a dimer or tetramer, are retained. So this would ensure that their good properties can be carried on. Okay, so our second approach was to further enhance the stability of these network structures by replacing the simple organic ligands by specially designed ones that have the highest bonding strengths between organic and inorganic components. Here I show you 3 such examples, 3 ligands specially designed and 3 hybrid structures, network structures made of these 3 ligands. Now, as you see, the decomposition temperature of these hybrid structures are much higher comparing to the molecular ones. Even with the lowest one is more than 300 degrees Celsius. And this strong binding strength is also confirmed by our DFT calculations. Here you see the binding energy between copper and the nitrogen of this ligand, the BMBIPE, which is this one in the middle, is 2.1 eV, which is 10 times higher than that for a copper-nitrogen bond made between the ligand pyridine. And so here you see a summary of these extended network structures built of the special ligands. Clearly, their emission energies and emission colors are tunable. Their quantum efficiencies are at least doubled comparing to the previous class. And their decomposition temperatures are at least 210 degrees or higher. So they are very, very robust. Now, for commercial applications, long-term stability is required. So let me also show you some results that we found. Here you see the data for thermal and moisture stability test. The y-axis is a change in quantum yield as a function of temperature and time. Okay, so at each point, the sample is heated for 24 hours a day. Okay, and so going all the way from room temperature to 200 degrees Celsius. Now, for the 2 compounds showing in red and black from this pile, as you see that their performance is reduced very little, okay, even at 200 degrees. However, for the molecular compounds here showing in green and blue, their quantum efficiency dropped by 80%, only at 150 degrees. So the difference is clearly seen. Now, for photostability test, we shine sample under a UV light source continuously for 30 days, okay? And here at the bottom are the results. Now, for these 2 same compounds, as you see that their performance is retained, almost very little change, very little decrease. However, for the molecular compound, in 5 days, they are dropped by at least 40 to 80%. So as you can see that these two approaches are very efficient, creating high performance structures with high stability. However, we want to do better. This is because the specially designed ligands are quite involving in terms of their synthesis, so that would lead to higher costs. And also extended network structures, as many of you know, have a very poor solution processability. So they would not be good for device fabrication. So that problem, very recently, we have developed a brand new subclass of the copper halide-based hybrid structures. We call these all-in-one or AIO compounds because they contain all three types of bonds: ionic, covalent, and coordinate. Okay. As I mentioned earlier, the molecular species that composed of coordinate bond between inorganic and organic species have high luminescence. However, they're not very stable. Now, for the pure ionic compounds made of cationic ligand and anionic copper halide molecular species, the stability is very high, and they are soluble in some solvents. So the idea is, if we can combine these two into a single crystal lattice, we might be able to bring in all the good features into that single structure, right? So this actually took us a very long time to achieve, almost 3 years. But I'm very glad to tell you that we finally succeeded in doing this. And here I show you some examples of simple cationic ligands. They're very easy to make. And also some examples of anionic inorganic modules. Next slide are some examples of the zero molecular AIO type structures that we have synthesized and characterized. In all of these structures, the inorganic modules are molecular anions. And here are examples of one-dimensional AIO structures where all the inorganic modules are one-dimensional anionic chains. Here again, I show you a table summarizing the most important properties of these compounds. As you can see that again, their emission energies are fully tunable. They have the highest photoluminescence quantum yields. They are very robust with a decomposition temperature that's high at least 220 degrees Celsius. And we also did long-term stability tests on these compounds. As you can see that they are performing even better than the previous group. More importantly, all of them are soluble in selected solvent. So now we can coat them on just about any type of substrate that we want, whether they are flexible or rigid. And we can also make them into freestanding films. So by far, this subclass represents the best candidate for phosphors. And later on, I will show you some prototype LEDs using some of these as phosphors. But now let me switch to type 3 hybrid phosphors, namely LMOFs. Here I will focus on just 2 subgroups. One of them are made of highly emissive chromophore ligands, and the other type contain multiple emission centers, and they emit white light. So for chromophore LMOFs, our strategy is to immobilize, I forgot this one. So for MOFs, just in case some people may not be familiar, there are a variety of different type of emission mechanisms shown here. Now, the 2 subgroups that I will be talking about, their emission mechanisms fall into one of these 3 types or a combination of some of these. For chromophore LMOFs, our strategy is to immobilize ligand into the MOF backbone. In these cases, the metals will not contribute to emission, but only serve as connectors or studs to fix the ligand in place. So the emission will be ligand-based, but we expect greatly enhanced luminescence because of effective reduction of non-radiative decay as a result of suppression of molecular motions of these ligands, such as vibration or rotation. Now, I mentioned earlier that the simplest white LED can be made by a blue chip with a yellow phosphor. So here I will show you an example to demonstrate how we design a highly luminescent yellow emitting LMOF using a chromophore ligand. To select a suitable candidate of a ligand, we again turn to the theory. The DFT calculations show that this molecule, TCBPE, has a suitable band gap, and indeed this molecule emits strongly a bright yellow light with an internal quantum yield of 62%, which is very high under the excitation of a blue light. So with some effort, we're able to synthesize LMOF 231, built of this ligand with a zinc as a connector. On the right side, I show you the excitation spectra on the left and the emission spectra on the right for the ligand in black color and for MOF in red color. Clearly, the MOF has a ligand-based emission, but the internal quantum yield is increased by 25%, which is very significant. Okay, and at bottom, I also show you the excitation and emission profiles of LMOF of this MOF with the benchmark yellow phosphor YAG-CE. As you can see that their emission profiles are very similar, indicating that they have a very similar color quality. Now, this is not an isolated case. It works for other metals as well. Here I show you two other examples made by bismuth and indium with the same ligand. In both cases, the photoluminescence is greatly enhanced comparing to the ligands. Okay, so this approach works very well in generating highly luminescent LMOFs, but there is a limitation. That is that it has very poor tunability in terms of emission energy. This is because once the ligand is selected, the emission energy is fixed. So in order to add, okay, I was going to skip this, but let me quickly going over here just to show you we can also functionize the ligand to further enhance the luminescence for that TCBPE with zinc. We put fluorine onto this ligand so that that has a lower LUMO and HOMO. And combining the two, partial replacement of TCBPE with the fluorinated one would lead to reduced optical band gap of the new MOF, so that it makes it much more blue excitable, okay, because the chip is blue. And so here we gain another 13% of it, the quantum efficiency. Okay, so now let me come back to how to solve the problem with the tunability of emission, color emission energy. In this case, we introduce a second ligand, which we call band gap modulating ligand. Let me give you just one example here also. In this case, let's select the TPPE as a chromophore, which also has a high quantum efficiency, 57%. However, you might notice that it's not emitting a yellow light, it's emitting green light. Okay, so in order to use this as a yellow phosphor, we have to red shift the emission energy, right? We need to tune the energy. To do that, we introduce this co-ligand BTC, benzene tricarboxylate. Our calculations show that BTC has both lower LUMO and HOMO energy comparing to the chromophore molecule TPPE. Combining the two ligands into a single MOF structure would allow us to decrease the optical band gap, so that making it a red shift. With some effort again, we succeeded in making this MOF, LMOF 251, and our optical spectral experiment confirmed that for this MOF, the optical band gap is decreased by about 0.3 eV comparing to TPPE, the chromophore. And this decrease not only leads to the red shift of the emission going from green right into yellow, it also red shifted is a excitation spectrum, making the MOF much more blue excitable. See, 450 is the blue wavelengths. And so with this, we gained a remarkable increase in the quantum yield, 34%. And that is outstanding achievement. And so here on the right side, I also show you the profiles between LMOF 251 and the YAG-CE. The two emission spectra are almost overlapping, again, indicating very similar color quality. Here you see a summary of the internal quantum yield of these two MOFs, as well as their external quantum yield, which, as you see, they are very similar to the internal quantum yield, indicating that both MOFs are excellent photon absorber. We also made the two prototype LED bulbs in this case, and their lumens per watt. These are the figure that you see on the commercial package. Well exceed the threshold set by EPA's Energy Star program by the United States. The number there is 40 lumens per watt. Here on the right side, you can also see the actual samples of the two under daylight, and this is under blue excitation. Even the powder look very similar. Okay, so continuing with these results, we made different combination of chromophores with band gap modulating ligands, and we successfully synthesized a large number of LMOFs. Here I show you again 5 examples. As you see, I like 5. And here is a summary of these LMOFs. Again, their emission energies are totally tunable, and their internal quantum yields are very high, and much higher comparing to their corresponding chromophore ligands in all cases. Okay, so now for the second group of LMOFs, our goal is to make white emitting structures, white emitting LMOFs. Again, as I mentioned earlier, we can make a PCYA LED by a UV chip in conjunction with multi-component phosphors. For example, a yellow phosphor with a blue phosphor, or a RGB combination, red, green, and blue. Or we can also use a single white emitting compound in conjunction with a UV chip. Okay, so these ideas can be applied to the MOF structures as well. For example, we can have a framework that emits, let's say, a blue light in this case, and we introduce a gas molecule that emits yellow light. So yellow, blue, like this way, would give white light, or vice versa, a yellow emitting framework with a blue emitting gas. Okay, again, let me show you an example how we make such a MOF. In this case, the structure is made by a metal cadmium with a hexacarboxylate, TATPT. The structure has two types of pores shown here with the sizes. The framework is a anionic structure which emits strong blue light. So we selected a iridium complex cation which emits strong yellow light. Now we incorporated this complex into the pore by ion exchange through a post-synthesis procedure. And by adjusting the amount of the complex in the pore, we can fine-tune the color. Okay, so this is the amount of cation, the complex cation increases, the peak increases, so that we can go from a bluish white all the way to yellowish white. So this way means this way. All right, so this works well, but the post-synthesis approach often suffers from a leaking of the gas molecules because they can come in, they can come out. So to avoid this from happening, very recently we developed a synthetic strategy to encapsulate luminescent gas molecules through in situ formation of the framework. In this particular case, we use diff8 as a MOF host, which has a cage-like pore. So small opening, but a big cage. We selected 3 dye molecules, red, green, and blue, in that all of these have their molecular size smaller than the cage so that they can fit in, but larger than the opening. So as soon as they are captured, they cannot come out. They cannot leak out. We use the 3 different models to synthesize these nanocomposites. Let me just show you one of them. So this one, model 3, first we process a nanocrystal of a diff8 with 1 dye, blue dye, and then we add a shell with green dye. We add another shell with red dye. So all 3 of them are incorporated. Here the SEM show you the images of a single dye, 2 dyes, and 3 dyes. On the top, you see the photoluminescence spectra of a single dye crystal, and the combination of the 2 dyes are all shown here. And on the right side, you see the 3 dye combination, where we also adjust the amount of 1 dye to tune the white color. And PXRD patterns show that in all cases, the structure is very robust. Crystallinity is retained. So with this approach, not only we achieve the white emission with high performance, we can trap the dye inside without leaking out. Okay, so with all the good phosphors, we were able to fabricate some prototype LEDs that I show you here some examples. And this is the first generation of bulb that we made. Believe it or not, these are really just the round bottom flasks. We use these as our bulb. And these are a second generation. And I wanted to show you our latest generation by just a 1-minute short video. Okay, so here first is the assemble process. Right, so we use a commercial chip, 120 volts, few watts, very low power, and we coat our phosphor onto the chip. And for form the bulbs. Here are two white bulbs. One is commercial from the market. One is our homemade, homemade with our phosphor. See if you can tell which one is which. Let's turn on. So lamp 1 and 2. Okay, and get one homemade. See if you can tell. Now for the front of it, I show these LEDs. So here are okay. So much for that. And now I think it's a time to wrap up. So I hope that I have demonstrated to you that that with very high luminescent performance and excellent photo, thermal, and moisture stability, these hybrid phosphors are indeed a very promising candidate as alternative phosphors for energy efficient lighting technologies. Our studies also show that these materials exhibit very strong structure property correlations. They are very interesting and unique luminescent properties are really a result of interplay between inorganic and organic components. Their electronic, their optical and the thermal properties can be systematically tuned and optimized by engineering the crystal structure, the chemical composition, and the bonding at the inorganic and organic interfaces. So our future study will focus on a more in-depth understanding of the mechanism of the luminescence. And so hopefully this understanding will guide our future effort in further enhancing their properties and performance. And eventually we hope that we could push that into the commercialization. And with that, I would like to thank my team members for their hard work and dedication. First and foremost, my students and the postdocs, and also my collaborators and the visiting scholars. And with that, I thank you for your attention, and I'm happy to answer any questions that you may have. Thank you.
Thank you, Professor Lee, for this wonderful talk and sharing this information about the new materials that you have developed for the energy efficient lighting technology. If you can please come on the video. So we want to see you. And then I think Professor Lee would be happy to take a couple of questions. We have time for, yeah, actually we have more time. So
We do?
yes.
I went fast. I was afraid that it's going to go
And we started a little early than the scheduled time. So
okay.
if anybody's having questions, please you can turn on the microphone and ask the questions.
Hi, I see your hand, but the microphone is mute.
Yes, I see Abhijit Ajara.
Hello. Hello,
You can go
ma'am.
ahead.
May I audible to you?
Yes, yes, yeah, go ahead.
Okay. Thank you, ma'am, for this wonderful presentation. I have just few queries rather than say question. Ma'am, first of all, you showed that you have incorporated some dyes in the chip of framework. May I know what is the driving force for incorporating such a large molecule in that cavity with maybe the steric hindrance? How will you minimize the steric hindrance effect?
Minimize what?
Steric hindrance.
Oh, No, there is no problem. Okay, so first of all, the reason we incorporated these dyes is because they are, they belong to this type called aggregation coarse quenching. So they can only be used, in the solution, they have a high luminescence. However, for lighting purpose, you cannot use a solution. So in the solid state, they almost do not luminesce at all. And so incorporate them into the MOF pores would eliminate aggregation. So that's why that we achieve a very high performance. Now, there is no steric hindrance in this case, because each cage is we measured, it will hold one molecule without any problem.
Okay, so as the is like a mesoporous material, so how can I design such a kind of port that fits a different size of that molecule?
Yeah, I mean that's the magic part for metal organic frameworks. Essentially, you can design just about any structures with any type of any size, any pore size, any pore shape. And the different type of pore surfaces. You can functionalize the ligand so that you can introduce a functional site into the pore wall. And that's why that the field is has attracted so much attention.
Ma'am, another small question about that about the luminescent LEDs. So you have maximally chosen the copper as your prime metal. So is there any specific reason for that?
I'm sorry, I couldn't hear what you're saying. Can you go a little bit slow?
Okay.
I think there's a lot of feedback. That's why I cannot hear very well.
Okay. For your luminescent material, you have primarily chosen copper is your prime metal. Is that any specific reason for that?
Why choosing copper?
Copper,
yeah. Oh yeah, I mean copper iodide. These are the cheapest. Really, I mean, when you compare with many other metals, this is a very cheap copper iodide based structures and very easy to synthesize. We can just make it by stirring at room temperature. You can easily scale up, right? And everything, there's no toxicity. So that's a very good good combination.
So there is a many dimensionality among that kind of material. So what is the preferable dimension? Should I go for the 0 dimensional or 1 dimensional or higher dimension?
So your question is what is which one is better, high dimension or no dimension?
Yeah, ma'am.
Okay, yeah. I thought I went through that. Okay, so for a device fabrication, usually, okay, I mean, phosphorus is slightly different because it's just a coating onto a chip. But for most of the applications, you wanted to be able to solution process, right, the device. And so high dimensional structures, whether it's covalent or coordinate, they are no good. They don't dissolve. And so solubility is a big issue. But high dimensional structures are very robust. So I thought that I talk about these issues, but maybe I went too quick. And so that's why that, we develop this AIO type of structures where I demonstrate even with a high dimension, like a 1D or 2D, we can still dissolve them. So that is very significant. So that's why that we can now use these materials. In fact, our future study, I'm going to use the same materials to make the actual film device, okay? And because they are soluble, we will be able to process thin films without any issue. Molecular compounds are usually not very stable, right? So I demonstrated that. And so there's pros and cons, but they are more soluble. And so it depends, right? So you have to see what is you really need.
Okay, I see one more raise on hand. Professor
Thank you, ma'am.
Padmanabhan.
Thank you very much.
Yeah, hi.
Hi.
Tapu is my
Yeah.
old friend.
Good to see you. Thank you
So
for
glad to.
odd time for you, and then thank you very much for accepting our invitation and then sharing your wonderful work. I know that you added quite a new, new area into your thing compared to your 2,6 compound. This is more exciting.
I know. When you were in my lab, we were working on 2,6, right?
Yeah, I know. Thank you so much. And I have a few I wouldn't say questions, like probably clarifications. Your chromophore, which is a organic one containing one fluorine atom, fluorinated chromophore. I don't know
Yeah.
Okay.
Fluorinated chromophore,
So
yes.
I mean, you said actually that would reduce the LUMO, and you can tune your excitable this one from blue to probably a little lower or something. Or so I'm wondering whether you can steric wise it will not be a problem. You can have more fluorine atoms onto it. You can modulate that electronic structure of that chromophore, and you can have excitability in lower region, probably in the UV region also. Is that has been tried? I mean, I don't think it will cause any kind of a steric problem, but if you have a more,
So let me, first of all, when you have a fluorinated TCPP, okay, that ligand, regardless of how many you put in, the portion of replacement of the parent ligand, the LUMO energy level is fixed for fluorinated ligand, okay? It's just the amount of replacement, the portion of replacement may be changeable, but the energy level will be fixed. So that means that whether I have 20% or 40%, the resultant MOF would have the same optical band gap, okay? But with this case, actually, we found that the highest that we can incorporate is about 20% of a fluorinated ligand. But if you wanted to, let's say that if you wanted to tune the energy, in this case, we're not trying to tune in the emission energy. The emission energy is the same because the fluorinated ligand has the homonumal gap same as the non-fluorinated one. But in this case, we wanted to make the MOF more blue excitable. By that, I mean that when excited by 450 nanometer, that we wanted to have high luminescence. In many MOFs, okay, I didn't mention this, but in most of the MOFs that people have been working on, whether it's coordination polymers or MOFs, they might have a very high luminescence quantum efficiencies, but many of them must be excited by high energy, like UV energy. And that's not good for LED, okay? For white LED, the current technology uses a blue chip. So you must use a blue light to excite your phosphor. So many MOFs are out because with the blue excitation, they have a very poor luminescence. And that's why that we are decreasing the optical band gap so that more photons will be absorbed under blue excitation and increasing their performance.
Okay, perhaps that's the reason why you omitted the chlorine and bromine, because probably that will be excitable in the UV range.
Bromine?
Yeah, chlorine and bromine. Cuprous chloride and cuprous bromide. You omitted that part and you talked only about cuprous iodide. So is that the reason is the reason is because you don't have a blue excitability in those?
No. That's totally different. Copper iodide are not the what you were talking about just now are MOFs. Okay, copper iodide.
Not MOF. The same analog, because structurally they must be same copper iodide and then copper 1 chloride and copper 1 bromide.
Yeah. Okay. But
Yeah.
let me clarify this. So for copper iodide, copper bromide, copper chloride-based structures, okay, they are different from what we were talking about with MOFs. And so in their case, actually, for if you replace iodine by bromine, in fact, you observe something very strange. You actually have red-shifted emission, slightly, not much. And so if you go to, go up the periodical table, you actually have a redshift. Okay, that's actually very interesting. We have not totally figured out why is that.
I have seen your KenCom paper, which is silver and copper combination, and you can incorporate silver into copper, silver iodide, and then copper iodide. Are these isomorphous, isostructural copper?
Some of them, yes.
Okay,
when you replace copper by silver, you are going to have a emission in a higher energy region. Okay, so in this particular case, especially for white LEDs, we typically don't want to go to silver. First of all, we don't want it to have a higher energy. We want it to have a yellow, red, orange, right? Because they are needed for a blue chip in order to make a white LED. Now, also silver, of course, is more expensive, and so we have not worked much with silver. But silver halides also form similar structures as copper halides. The hybrid structures we have not worked much.
Okay, perhaps just small question. Okay, you see fate and you have a dye getting incorporated into the cavity there. If you can do the synthesis of C8 in presence of the dyes, you need not do any post-synthesis modification. You can perhaps start preparing the CIF8 in presence of the dye, and the dye, the cavity of the CIF8 is comparable to the size of your dye. I feel that you can easily get into that void and then get the combo, get the hybrid material without any kind of post-synthetic modification. Has it been tried?
I'm sorry, I didn't totally get your question. Post the synthesis of what?
You said actually you incorporated dyes into the CIF8, that dye combination. Yeah, CIF8.
What do you mean? Oh, CIF8.
Yeah, CIF8. Yeah,
yes, CIF8. Yes,
and,
yes. In situ.
Yeah, in situ. Yes. Did you try in situ or after post synthesis?
Oh no. Okay. Again, I think maybe I went too fast. We did in situ because of post synthesis procedures. The dyes can leak out very easily. Because since you do it at post synthesis, that means that they have to go in, and then if they can go in, they can come out. But with in situ is different because of the cage-like pore.
Okay. Oh, okay.
Once they are trapped in situ, they cannot come out.
Okay, I thought you do the post synthesis.
No, in situ.
Okay. Yeah.
Yes.
Okay. Thank you.
Yeah. Thank you.
Thank you once again, Professor Lee, and then. I really enjoyed the stay with you those days in 2006, 2009.
Thank you, but you asked too many questions over time. I'm sorry for other people.
No problem. We started early, so we had that time. Thank you very much, Professor Lee, for taking part in this conference. I know it must be midnight for you. So
yeah, it's almost midnight now.
Yeah. Thank you very much for your time and all that knowledge you shared with us. Thank you. Thank you very much.
Thank you.
You have a good night.
Well, for you it's the morning. Have a good day.
Thank you. Okay, so now we'll move to our next keynote talk. We have Professor E.D. Jemis with us today. I think Professor Jemis is here. Yeah, I see him. I request Dr. Sridhar to give a brief introduction about Professor Jammis.
Namshivaya, am I audible?
Yes, ma'am.
Okay, good morning all the participants. It's my honor to introduce our next speaker, Professor E.D. Jammis. E.D. Jammis is a professor of theoretical chemistry at the Indian Institute of Science, Bangalore, India. He was the founding director of Indian Institute of Science, Education and Research, ISER, Trivandrum. His primary area of research is applied theoretical chemistry with emphasis on structure, bonding and reactivity across the periodic table of the elements. Dr. Jammis was a visiting fellow at the Australian National University, Canberra, and a visiting professor at the Center for Computational Quantum Chemistry at the University of Georgia. Dr. Jammis is an honorary professor at JNCSR and adjunct professor at ICTS TIFR. In 2005, he joined the Department of Inorganic and Physical Chemistry, and in 2008, he accepted the responsibility to start ISER Trivandrum. Dr. Jammis superannuated on 31st July 2017 and continues research and teaching as honorary professor. He has mentored more than 20 PhD students and several postdoc students and research associates, and he published more than 200 research articles. His number of citations now crossed around 8,700 and an H-index of 48. His memberships and honors include Fellow of Indian Academy of Sciences, Shanti Swarup Bhatnagar Prize, Fellow of the Academy of Sciences, J.C. Bose National Fellowship of the Department of Science and Technology, Professor T. Navneet Rao National Best Teacher Award, TWAS Prize, and also our nation honored him with Padma Shri in the year 2014. We are highly honored to welcome you, sir, for the talk. The title of his talk is Benzene to Boropene and Everything in Between. Over to you, Jammis, sir.
Thank you very much for the kind introduction. It's always a pleasure to be in a group of people that are familiar. In fact, I see Professor Nandakumaran and Professor Padmanabhan I know early on. And thank you, Professor Kulkarni, for the kind invitation. Let me not spend any time. I would like to make sure that my colleague who is going to speak next would start on time. And in fact, I am also pleased to really follow Jing Lee, who studied with Professor Hoffman. I studied with him 30 years earlier. So it was very nice to see that. I have, I think the screen has come in. Yes.
Yes,
so
sir, we can see.
Yeah. So it is a pleasure to be in this international conference on advances in material science and chemistry. I have noticed that the scope of the conference is large, and after giving the title, I realized that I have to possibly make these come very close to many interests, and so instead of giving a large detailed analysis of many things, I would rather give a set of connectivities between compounds or allotropes of boron. The reason is that, when you look at the periodic table of the elements and decide what to say, and then you look at the possible topics that are invited for the conference, it is all of chemistry, and I will make an attempt to get at least a little bit accessible to most people who are listening. I would say that we know all about carbon, but we do not know much about boron. So I'm just looking at chemistry in general as a textbook, and what I could see. When I see carbon, you can easily see that most of you are familiar with the relationship between sp3, sp2, and sp hybridization in carbon, the way diamond could be generated, the way benzene through Huckel-Foren +2 rule going to naphthalene, and if you essentially extend it to graphene, of course, graphite is here. We had fullerenes. In essence, even at the BSc first year level, the structural relationship between the carbon as an atom's behavior and properties of the allotropes and molecules are easily understandable. And in fact, this occurred to me, that there is something so very orderly. When I was a student in the university college in 1968-69, it's only, probably about 60 kilometers from the campus of the university here. In my there was a really very enjoyable professor we had, Professor Shankara here, and he discussed in great detail the beauty of this carbon structural chemistry. And I happened to ask in a very innocuous way, is there anything like this for boron? And this teacher was very much interested in answering these questions. So we looked through and we looked through and we looked through. We couldn't find an answer. In fact, I carried on this question with me even as an MSc student, and later on even at PhD for Princeton. I couldn't really put my hands on, and I couldn't find this relationship. Just as carbon, methane to diamond and benzene to graphite, I couldn't find it for the next 30 years. And of course, I worried about the problem, but you cannot just worry about the problem, but you have to have problems. So I give this slide more to the students that one should always think about problems. Some of them, when you ask and, asking a question and get the answer, you find that it is already known. But there are questions that are largely around, especially when one begins one's studies, that you could make a list of them and then carry on with it, so that at any stage around here, you don't really work for or look for problems of some kind. So it is nice to ask questions early on. Now, I said I didn't find an answer till 2000. Of course, I did many other things in this period, otherwise I wouldn't have even got a job. So I did other things, many other things, and I was thinking that I would probably talk about hydrogen bond and other weak interactions in the context of materials. But I decided that there are many, many different areas represented in this conference probably, and I should not really be risking talking about just one thing. So I thought of the most general one, and as I went along, the simple question, is there anything like this for boron, took a more definite set of questions, and I started looking at this in greater detail. So today, I would say that yes, we have seen all of these carbon chemistry and we assume that everybody knows this. But if we were to think about the next element, how much do we know? In other words, just as the extent of knowledge that we have on carbon, which is known to everybody in chemistry, really even at early level, such a structural chemistry must exist also for boron. And this attempt here will be to make it simple enough that each one of you would have a glimpse of what is possible. And I said benzene to borophene and everything in between. Of course, benzene to borophene sounds like some transmutation. It is not transmutation, and I will show you why I say this. Because let's start with benzene. I have purposely removed this circle that we normally add. We remove 2 electrons and we have the benzene dication. Benzene dication was first made by Hoggeveen in 1975. People didn't believe it existed, even though he had all the spectroscopic evidence. In fact, he was chided for it, and the professor was almost mentally dejected by this. But only 3 years ago, we have an X-ray structure of benzene dication. Instead of hydrogens, we have 6 methyl groups instead of 6 hydrogens. This is interesting. It is interesting because, it is so close to inorganic chemistry. Why is it close to inorganic chemistry? If you replace this dication by an isoelectronic C5BH6 plus, it becomes a monocation. This has a pyramidal structure just as this, but we don't see this often in organic chemistry textbooks, but inorganic chemistry. If you replace 2 of them, we have C4B2H6, which is a carborane, and organic chemists will say, okay, this is inorganic chemistry, even though there are 4 carbons. And we can keep moving like this. If you replace all the borons, we have B6H6 4 minus. Of course, this is not very stable, but if you protonate the 4 BB bonds of the square, of the pentagon, Then we have B6H10, which is also very well known. This is very well known. It's made long time back. MgB2 is treated with acid and you get B6H10, B5H9 and so on. We'll come back to MgB2 later on, but it's interesting why these are more stable. I can say, of course, in benzene we have 6 pi electrons, and I say these are stabilized even further when you come to a 3-dimensional structure. But how do I prove that this is true? I come back to simple molecular orbital picture. We have H2, 2 hydrogen atoms giving H2, and we have an antibonding level. In a similar interaction diagram, we take a ring of the C5H5 and the cap as CH, and then you see that the 3 pi MOs that we have, they are stabilized further if you have a group that is coming at the top. A p orbital here, sp hybrid interacting with this particular lobe, in the top lobe of the lowest pi MO, and these 2 p orbitals interacting with these 2, and so we have stabilization. Nothing complex. This has been known for long. And we say, of course, this is now aromatic, obviously, because it is even more stabilized, and we say 3-dimensionally aromatic. And it is actually reflected in B6H10. B6H10, we have already come to boron from benzene. There is, of course, C2B4H6, which is carborane. Now, we could do this exercise and remove 2 more electrons, and then we get to C6H6 plus 4, not quite stable, but the isoelectronic C2B4H6 or B6H6 2 minus are well known. Now, we can do this not only with benzene, we can do it with a 5-membered ring, a 7-membered ring, tropylium cation and cyclopentadienyl anion. We can get equivalents of B7H7 2 minus, B6H6 2 minus, and so on. In fact, a whole lot can be done if we just expand this diagram to see what all things that it can go to. In fact, if you can put 2 of them together, you get to a 14-vertex system, which is known in metalloboranes. You could, of course, consider 2 of them coming together for becoming an icosahedron that I will come back to. You can get in this path going all the way to boroscenes, and there is a lot more that we can learn from this general picture. We can say, well, how do you get to B12H12 2 minus from B6H10? Well, put 2 of them together. Put up 2 of them together with the 5-membered ring phase coming to each other, and we have a structure like this. We can say, of course, what is the electronic structure? Why is it B12H12 2 minus? Many ways of doing this. I will take the simplest that is familiar to you. All of you would have learned Wade's rule. Well, at least those who have taken advanced in organic chemistry courses. And Wade's rule essentially tells you that if you have a BN-HN polyhedral structure, we should have n+1 skeletal electron pairs where we have n vertices. An additional electron pair is brought in by the -2 charge. A simple way of doing this will be you take BH and BH groups, each would have 1 sp hybrid, so n sp hybrid directed to the middle of this centroid of this polyhedra, and at least the all plus combination should be stable. Then, of course, n-1 which are less stable. We have also 2n p orbitals of this kind, which forms the surface bonding, and out of this 2n there should be n bonding combination and n anti-bonding combination. These n+1 is the number that we required for the skeletal electron pair count. This is just one of the simple ways of justifying it. So why do we still talk about B12H12 2 minus? We have other polyhedra in constructing the allotropes of elemental boron. Well, we can say, why start with benzene for graphite, which is, of course, the thermodynamically most stable allotrope of carbon. But there are more interesting reasons. In fact, B12 is the best icosahedra that one can have, best polyhedra that we can have in boron, and only in boron, really speaking. And there is a reason which is based on orbital engineering, and I wouldn't spend time on this today. But come back to this slide I had given in the abstract. We start with this, and we can, of course, go to the simplest of the polyhedral borane, that is alpha rhombohedral boron. I will do that. It's very easy to understand. It's a lot more complex to get to beta rhombohedral boron, which is thermodynamically the most stable one, or tau boron, which is the next best one, because we have to go through a way of condensing polyhedral boranes, which obeys the n+1 skeletal electron pair rules, to come to condensed polyhedral boranes like B6H10 and B20H16 and so on. So I may not reach to this part of the talk because I would like to talk about things that are far more simple. If you remove all the hydrogens, we get to a flat structure like this. All it's a trianguline kind of a structure, only triangles. And this, of course, if you expand in 2 dimensions, we have roughly a graphene-like structure. And when we really look at this in greater detail, we get borophenes with some holes and so on. So I would concentrate on this part in the initial lecture part, and possibly may reach this part. If I do not reach, it doesn't matter, because the attempt is to give you something equivalent of the carbon chemistry, which is understandable to most people. So alpha rhombohedral boron, as I said, is the most easy to understand. Why is it? Because we have already seen H2, and if we have H3, we see that H3 plus could be very stable because we have a bonding molecular orbital. 2 electrons are sufficient, and then the antibonding ones are not filled. If you look at B12 icosahedra, you find something interesting. You have removed all the hydrogens, but we have these orbitals sticking out, right, from each of them. Now, what has happened in alpha rhombohedral boron is that from these 3 borons, each of these ones, there will be 2 center 2 electron bonds to other B12 units above it, and from these 3 boron atoms, there will be 2 center 2 electron bonds to other B12s which are behind it. But these peripheral ones here, they would have 3 center 2 electron bonds. In other words, you have an electron because BH is broken away. You have an electron, you have another electron, a third electron. But when you form a 3 center 2 electron bond, you need only 2 electrons, as we saw in H3+. So we have an extra electron. Now, this extra electron is important because according to Wade's rule, each of the B12s should be -2. And we save for each B12 unit, we save 2 electrons. And so alpha rhombohedral boron is actually electron sufficient in the sense of Wade's rule. And this is seen in textbooks because it is easy to explain. The beta rhombohedral boron, which is slightly more stable and thermodynamically the most stable allotrope, is far more complex, where we have to make B12s in far more complex ways. And so I would skip it for the moment and try to come to the flat structures which can be talked about much more easily. I said easily, but it also is very tricky in the sense that we have a polyhedral arrangement and we have to get to a structure which is flat. A structure for B12 without any hydrogens has been studied by a large number of people. They all have found that this is flat. We have just tried to see how that process takes place. If you remove hydrogens one after another, you could see what happens. If I remove just one hydrogen from B12 H12 to minus, just one hydrogen. If you remove one hydrogen, we essentially have 1 electron left, right? And the system is already B12 H12 to minus now becomes B12 H11 to minus, and it is a radical. But even if you remove 1 electron from here, it doesn't affect the internal delocalized electron picture. We still have n+1 skeletal electron pairs. So B12 H11 minus 1, which will also be like this. Now, if you remove one more hydrogen, something interesting happens because you have a possibility for a bond which is somewhat like a pi bond but not quite the same. And if you remove these 2 electrons, then also there will be the 2 pi electrons available. I mean, the extra 2 pi electrons, 2 electrons available here. So we have a B12 H10 which could also be stable. But this picture changes dramatically as we go along further and keep removing more hydrogen atoms. And I would not go through the details of it, but what one finds is that as the number of hydrogens removed increases, then the stability of the polyhedral 3-dimensional structure becomes less. In fact, as we go further, like 3 hydrogens removed, we still have a polyhedral structure that is the most stable one, but there is something very competitive, which is kind of a trianguline but linear arrangement. And there is, of course, a structure that is flat, almost like the B12 becoming competitive. You remove one more hydrogen, you have this actually more stable. And if you have removed one more hydrogen, then you have this as the more stable one. This is much higher. There are reasons why each one of it changes like this, but I'm skipping all these explanations today to get to the borofene structure. And so if you remove the last of the hydrogens, you get this without any question. Now, from this, if you want to make a graphene equivalent, see, we have a structure like this. We have just extended it. You know, it is all triangles and a two-dimensional structure. It's almost like graphene. If you take graphene and add an atom in the middle of the six-membered ring, each of them, it is like graphene. For example, I have just added these, blue boron atoms in the middle of each of the hexagons. This is the structure of borofene, an idealized structure, which is very closely connected to graphene. Now, this has been studied for long. In fact, one of the early studies of this indicated that, borofene of this kind has a binding energy per atom of about 6 electron volt. Now, it also shows that if one can take one layer of this, one row of it above, another row below, a third one above, and alternating queuing like this, the binding energy increases. What's more interesting is that if you could take one atom out of the adjacent six-membered rings, like I have taken one away, one from here, and so on, so that totally for every 9th boron atom, one of them is missing. If you have this, it becomes even more stable. Now, this was very interesting. It came out in 2007, and we were kind of looking at this. In fact, I had a PhD student, Dr. Prasad. He had actually the previous 2 years, he has worked on similar systems. And we thought, yes, we are understanding this. There should be some very clear ways in which we should be able to tackle this problem. So we thought we'll start with MgB2 and also study. So we studied, we studied borofene, but we called it borograph at that time. This is 2006. And when this study was really at its height, and I thought things would be really nice if I continue this, then I stopped work on boron for 5 years. There was not much of a choice because this work involved direct involvement of mine every day, and I couldn't do that from 2008 to 2013. So I stopped this and I came back to study this in 2013. And I had to start all over because Dr. Prasad had already completed his work and gone. Nobody else continued this work. And Dr. Prasad went to IIT Kanpur as an assistant professor. But in 2013, when I started again in boron chemistry, Dr. Navrid Karmotak, an MSc from IIT Kanpur in 2013, joined my group, and we decided that we will look at this again. And we found something very interesting. Between 2007 and 2013, large number of studies have been published, and all of these are references which I haven't given because there are very, very large numbers. And they have studied the stability of each of these different kinds of borofenes, varying the holes and structures. But each study was using a different functional, and it was not easy to compare them. So we decided that we will look at all of them and a few additional ones using just one specific functional of the DFT, and we can compare. When we did that, we found something interesting. Obviously, the one that was already shown to be the most stable one is indeed the most stable one, 1/9 hole density. This is just the hole density. I have changed it into decimals just to see the comparison. The flat structure is less stable, but what is interesting is that if you increase the number of holes, also it is less stable. In other words, there seems to be something unique with this 1/9 hole density, and that struck us something very unusual when we were looking at this in great detail. And at that time, all of it, in 2013, 14, 15, these were all, computational curiosities because all attempts to make borofene experimentally had failed so far. But then things changed. We wanted to, of course, understand this. Why we had to understand it? Because it looks as though, there is something that the system is telling us why this is more stable. Now, understanding means different things to different people. Coulson said, give us insight and not numbers. More recently, we say, give us insight and numbers. beginner said, look, it's nice to know if a computer program follows it, but he would like to understand it too. So there has to be some physical approaches in designing anything, even if there is quantitative results available. Otherwise, we will end up like this. We had made all the measurements correctly and then got the kernel like this. Now, that's something. And then when we were looking at this, something else happened. Suddenly, from 2005 onwards, there were a series of papers that actually claimed that they have made borosphene largely on metal surfaces. I have just given a selected set of experiments, and this review is most recent and it gives all of it. It's nice to see while we were looking through this, this happened, and we looked at it in great detail and see whether we can do kind of an understanding of this process. Now, this understanding that I'm talking about is accessible actually to even +2 students. So I would like to give this in a way that everyone understands it. Now, we come back to benzene, to C6, H6 +2 and so on, but we also go to a three-dimensional infinite solid picture. Well, with respect to benzene and graphene, we have MgB2. With respect to C4B2H6 and B5H9, we have MgB4. MgB2 is like graphene, except it is all graphene made of B- instead of carbon. And for every 2 B-, we have an Mg+2. It's an Mg+2 layer that is on the top. Here we have the pentagonal pyramids sharing an edge. One pentagonal pyramid, another pentagonal pyramid, and so on. And the open face of the 5-membered ring is occupied by Mg. We have, of course, MgB6, which is well known, like calcium boride, everyone knows. It is a 2-center 2-electron bond between polyhedral boranes. Each one is a B6 -2, and there is, of course, the Ca+2 or Mg+2 to compensate it, right? So this picture is helpful in this. How is this picture helpful? Let us come back to MgB2. MgB2 is like graphene. Each B- replacing a carbon, and for every 2 B-, there is an Mg+2. Roughly speaking, it's not as though the ionic character is there at all, but for a schematic way, we have a layer of the B- graphene and another layer of the Mg+2 ions, right? But now let us assume that we replace the Mg by a boron. Right? Now the boron, whether we get it as a replacement of Mg or a part of the B2, they are all the same. So we come back to this earlier structure where we said, let us put boron in the middle. Earlier, the Mg was above the ring. There were different atoms. Boron and Mg, larger atom Mg is above. But when you have all of them boron, we have a structure like this. Instead of Mgb2, if I take a ratio that is Mg3b6, it will be B3b6. Now, there is something unusual with this replacement of Mg with B2, with B. What is it? If you replace an Mg by a boron, we bring in an extra electron. Mgb2 was electron sufficient, so we have an extra electron here. Now, if we have B3b6, that is 3 Mg replaced by 3 boron, we have 3 extra electrons. Now, how do we get rid of these extra electrons so that we get to Mgb2? By the way, Mgb2 became a surprise because at -40 degrees it was found to be superconducting, -40 degree Kelvin, and something unusual. We replaced one boron. If you just remove one boron here out of 9, then we are removing 3 electrons. So if we have B2B6, then we have got back to Mgb2 electron count. That is 6 + 3, 9 boron atoms. Now we have one missing, 1/9 hole density. This is all to it, right? So 1/9 hole density really is an attempt by borosphene to get back to the electronic structure of Mgb2 or graphene. Now, this seems to be simple enough, right? But most of these experiments, they did not get the borosphene, a standalone borosphene. In fact, Ajay and Vinu and a few others now are attempting and succeeding to get standalone borophanes, but the initial first 4 years, there wasn't any chance. And all of them were on the metal surface. And so we thought we would also look at the metal surface. When we look at the metal surface, what happens? When we look at the metal surface, something interesting happens. We modeled it on a silver 111 surface because most of these experiments initially was with the silver 111 surface, and we find something very unusual. These relative energies that I was giving in milli-electron volt, in the absence of a metal, standalone borophene, this is the stability. We have the 1/9 hole density as the most stable one. We found that if you did not have any hole density, any hole at all, it is higher in energy. If you increase the number of holes, that also is not good. But the moment we come to a metal surface supporting a borophene, these are made by boron atom deposition on a clean metal surface. So it is as though one atom going and settling at a time and then trying to do it in such a way there is a monoatomic layer. And then you look at the surface using scanning tunneling electron microscope. That's the experiment. I will not go through the details of any of these things today, but to bring in the qualitative idea. But it looks as though the higher hole densities are more stable, and if you do not have any hole density at all, it is not as good. And as we increase the number of holes, it looks like as though the system is getting more stable. Now, why is that? It is not difficult to imagine this, and we have shown this using computational studies on the metal surface itself and looking at the density of states as a function of holes. And we find that as the number of holes increases, there is a possibility for the metal to donate. A metal like silver would like to make the system stable by donating, because its work function is not very high, donating. But to donate, you need to have vacancies to donate, right? Which means that you should have more holes than 1/9 hole density. So if you have more holes, it does go towards this. Of course, if you have it for gold, where the work function is very high, it is less likely that you have a flat structure with holes. In fact, it tends to be clusters, and of course there are manipulations that one can bring in, but you can never get large number of holes. Now this is nothing unusual once we look at it, but it was a while before people accepted this. Now, I could look at the properties, we have done some of it, of borophene on metal surface and so on. But my interest today is to give you the qualitative picture of a structural chemistry for boron. But this review that has just come out maybe a month or two ago gives all kinds of possibilities for borophene, which may surpass graphene in many ways. I say in many ways because borophene has the advantage in the following way. In graphene, if you want to make an electron rich or an electron poor, an N-type or P-type kind of a doping, we need to add other atoms. We need to add a boron or a nitrogen in graphene. But if you want to increase or decrease the electron accessibility in borophene, we don't have to bring in another element. We only need to bring extra holes or less holes. So this is very interesting. In fact, people are playing with it in many different ways. So, I could continue with graphene itself in many different ways. Like these two are easily understood by us. But what happens if you have more than one layer of borophene? Very interesting. I would mention only one thing about this, and that is if you have a bilayer, it's almost becoming like a graphene. Why is it? I'll put it this way. If you have a bilayer without any holes of borophene, see, this is borophene. If you have two of these layers, there is a possibility for the places where we had holes, those borons come down, or from the other layer it goes up and forms a BB bond. Now, once it forms a BB bond like these, once it forms a BB bond, there's something very unusual happening because you have localized that electron, right? So essentially, if we have one BB bond for every 9 boron atoms, then we are removing that many electrons and coming back to the structure of 1/9 whole density borofene. So a bilayer of borofene without holes is almost like borofene, and actually its electronic structure is somewhat like graphene. So these are generalizations I want to make without going to the details. About the metal surface, there is not much I need to say. But from here, where do we go? You know, the metal surface helped us to find that yes, some holes are needed and some holes are not needed. Can we do this in some fashion with 3D allotropes? You know, this is a part that I may have difficulty getting, but I will attempt because this is also equally interesting. I said we begin with B12. We did not explain why we begin with B12. I said there are reasons, and that will be a separate talk. But let us begin with B12 to make the most thermodynamically stable allotrope of boron. We did that for graphite, starting with benzene, which is the most stable aromatic system. Here, the icosahedral B12 H12 2- is the most stable one. So we start with icosahedral B12. We have already seen how without changing anything we can have alpha rhombohedral boron. But beta rhombohedral boron is more complex, but it begins with B12, and instead of completing B12 all around it, you know, it's a possibility. You attach a B12, another B12, and so on. But instead of doing that, because if we do that, we don't get a space filling model. If we stop it by half of an icosahedra, see, half of an icosahedra is of course pentagonal pyramid, right? That is how we made this in the first place. So if you put pentagonal pyramids all around, if you put 6 of them, you have a structure like this, right? We have B12 in the middle, then 6 pentagonal pyramids. But we have 6 more boron atoms here. If you do all of them, then we have 12 pentagonal pyramids. That means we have 12 pentagonal structures around a B12. Now, if I draw this, you know, if we did not talk about this, it would have been thought as though it is a fullerene. Actually, it has the same fullerene structure because there are 12 5-membered rings, which is there in fullerene, right? Except, you know, here we have only shown 6. Here we have shown all of them, but there is only one difference. There is 12 5-membered rings. Below each 5-membered ring, we have 1 boron atom, right? So there will be 12 boron atoms. So there is B60 right in the outside, right? Then below each pentagonal pyramid, pentagon, we have a boron atom. So that is the 12 boron atoms. And these 12 boron atoms are connected to an internal B12 polyhedron. So we have B12 inside a B12, the whole thing inside the B60. This is one building unit of beta rhombohedral boron. So, you know, you are structurally coming close even to a carbon allotrope, that is B60, C60. But the structure is far more complex. In fact, the attempt of boron is to make all boron atoms as much as possible a part of the B12, right? Another B12. So one way of doing that would be if you were to take 2 of these. If you were to take 2 of these, then 2 pentagonal pyramids will come closer as here, right? We have 1 pentagonal pyramid, we have a second pentagonal pyramid. So this forms an icosahedron. So bringing 2 of them, we generate more icosahedra, somewhat like this. The only problem is that, you know, B84, the only problem is that we only have possibility of bringing 6 B84 around 1 B84, right? Essentially 6 of them, which means that, you know, we can bring 1, 2, 3, etc. 6, but that will take care of only 6 of these pentagonal pyramids. The remaining 6 somehow have to be made into the form of a icosahedron. And how is that done? So nature has found a way. The unit cell is very large, Idealized one is 105 atoms. It has a beta unit that is left behind. This beta unit is very interesting. We have a pentagon here. We have another pentagon. Of course, these two are shared. Then we have yet another pentagon looking from this side. So we have 3 pentagons from this and a central atom here, right? So there are 3 pentagonal pyramids in some sense. If you keep this on the top of one of the B84, then we have again a pentagonal, I mean, an icosahedron generated, right? One icosahedron. I mean, it's a part of a larger structure, of course. And we can bring one here and one there as well. And that makes it a little bit more complex. But sure enough, you have a icosahedron, you have another icosahedron, you have a third icosahedron. Now the unit cell of, I mean, if you look at actually the 3-dimensional structure of beta rhombohedral foreign, you find something very interesting. It has a structure like this, the large one, connected to another one of the same kind through just one atom. And it's not so easy to make. So what I will do is, I will take this particular unit. You know, how many atoms are there? There is the B10, then there is B6, another B6, a third B6. 6 B6 is 18, 18 plus 10, 28. So a 28 atom unit like this connected to another 28 atom unit through one boron atom. So it's not easy to represent, but let me try. So we have a side view of this. I have taken B28, another B28 connected through one boron atom. Now, I have added hydrogens just to see how the molecule will also be there if you add hydrogens. Now this kind of describes the idealized unit cell. I will put it again. B104, 105, you can say B84, and then this B10 unit is connected to another B10 unit to a boron atom. Or if we count the polyhedra, we have 48 boron atoms of 4B12, and then we have the B28, B28. So we can say 4B12 and the B57. This I put like this, B105 and 4B12. You know, we already know from Wade's rule that it should have 8 electrons if you have 4B12, right? Minus 2 charge each. 8 electrons we should have. We have B28, BB28. We have no idea what is to be done with it. What is the electron count? And, you know, this is where, you know, I add the hydrogens and I have B57, H36, because these 3 plus 3, 6 boron atoms, I am not adding any hydrogen. So we have B57, H36. In a structure like this, what is the electron count possible? We have to then come back to another electron count. You know, in benzene to naphthalene to anthracene, we have Huckel-Farren plus 2 pi electron rule. For B12, H12 and other polyhedral boranes, we have the Wade's rule. We have no idea how to put these together because there are too many opportunities. We can have a 4-atom shared polyhedra B20, H16, 2 of them, or we could have 3 the triangular phase shared by the icosahedron. We have B30, H24. We need to have a way of finding out how these could be accommodated. And we had to introduce a new electron counting rule, which is not anything complex because it was earlier an n+1 skeletal electron pairs. That 1 is changed into m to have the number of polyhedra coming in. And we found that if polyhedra is connected to another polyhedra through just 1 atom sharing, it requires an extra electron pair. And all of these can be easily justified, but I just give you the rule alone. If you do that and take a triangular phase shared to icosahedra, we have, instead of one icosahedra is B12, another is another B12. It should have been 24, but 3 atoms are common, so we have 21, and these 3 atoms do not have hydrogen, so we have B21, H18 minus. So we have essentially number of polyhedra m equals 2. We have number of vertices 21, and here O is 0 because the connection is through a phase, not through 1 atom alone. So if you do this count, we have 2 polyhedra, 21 vertices, we have 23 electron pairs required. What do we have here? We have 18 BH groups, right? out of 21, 18 of them are BH. So 18 BH, and each BH has 2 electrons, right? So 18 electron pairs. And then there is 3 boron atoms. The 3 boron atoms, 9 electrons, so 4.5 electron pairs. So we have 22.5 electron pairs. In other words, we are needing another electron. So if this is to be made, it has to be an anion. And in 2001, it was kind of a risky prediction. Fortunately, another 6 years later, this was made and found that yes, it is B21H18 minus. And a lot of chemistry is now coming in because it's a highly reactive species, even though it is stable in terms of electron count. Synthesis is not so easy, but it is going on. If you consider, we can of course go and say naphthalene and anthracene. Similarly, we have all the other things. We can have 4-atom sharing just as usual. The 4-atom sharing is very interesting because this particular molecule was by accident synthesized by Lipscomb. He got an X-ray structure, and he was not used to having condensed polyhedral boranes. So he published a communication in JACS in 1968 and left it. He never proceeded further. If he had proceeded further, a lot more of interesting connections would have been established by Lipscomb. And Lipscomb is no unknown person in chemistry of boron. Lipscomb got a Nobel Prize in chemistry for studying the electronic structure and experimental studies of polyhedral boranes. I can go on and on, but it is it is my endeavor to make sure that I will not delay the beginning of Dr. Radhakrishnan's lecture even by a minute. So I would, try to get through the lectures very quickly and get to the end. Because it is not very important that I teach you a lot more about this, but to tell what more is possible. See, I stopped at this stage at one point, and I wanted to say that I wanted to say that basically, while doing this, we have now got into another set of allotropes of elemental boron. Many others have looked at this, but I feel that it is time for the chemistry of boron to take off like fullerene, even structures like B40 and so on. So there is a level of chemistry that is not discussed and thought about initially, and it is absolutely essential. It is absolutely essential that this becomes a general topic, because it took 100 years for carbon chemistry to come where it is, and chemistry of boron, especially elemental boron, is at that stage about 100 years ago what graphite was. So with this, I would thank my students who over the years have changed, I would say, or made meaning out of very vague thoughts of mine. And I would also thank Professor Sudhir Kulkarni and colleagues for inviting me, the IPC department, the Supercomputer Education and Research and the CRB for helping me with various funding possibilities. And I really thank all of you for listening, those who are at the campus in the university and outside. Thank you very much.
Thank you, Professor James, for taking us through this wonderful journey of your research in boron chemistry. I think we are running out of time, but we can take one question. If anybody has to ask anything. Professor James, if you can please come on camera.
Yes, let me see. Yes.
Okay, I see one raise on hand. Is it Professor Padmanabhan?
Yes, Professor Padmanabhan, speak on.
I see.
You have to unmute.
He has to do it. So. Okay.
Oh, sorry, am I audible now?
Yes.
Okay.
Yes.
So you talked about the benzene dication, and you talked about the structure which they have, in fact, experimentally found. Actually, it's a pyramidal. I mean, it's a pentagonal pyramid.
Yes.
So I was wondering whether, and you said actually the CH3, instead of hydrogen, you have a CH3 group. And I assume that CH3 is there because CH3 is electron pushing, and that might really take care of the +2 charge actually to some extent. So I was wondering whether your boron compound, the one you have envisaged or rather working on, whether they can be stabilized by the introduction of the, instead of hydrogen, you can have a CH3 group, and that will be electron pushing, and that will meet the demand of the electron deficiency that the boron systems have. Has it been tried experimentally and then
there are large number of derivatives of boranes, whether it is polyhedral boranes or otherwise made. For example, B12H12 2- is a very stable one, but you could make it even more stable by taking B12 Me12 2-. In fact, ionic liquids are having the anion component often as C B11 Me12 -1, right?
Yeah. Okay.
So it is not as though one can stabilize B12 Me12 neutral, because the extent of electron donation from the Me is not sufficient to get you -2 charge. But if one has the Me, it stabilizes it in two different ways. One is, of course, the CH is less reactive than BH, and so we have ionic liquids which has the anionic part, the borane anion. So this is something that is currently used.
And also, it's good to know that sharing. Thank you for sharing that information. You said most of these electron deficient compounds are physically characterized on the metal surface. Perhaps I assume the reason is that you have a low ionization potential of the metal thing, lose electron, and that can probably stabilize the boron or whatever the electron deficient system you have. Perhaps that's the reason.
That is a message for borosine, but not for boranes. Boranes have their electrons. What they want is already there. There was this great statement that was made by, I think it was Professor Grimes, who was writing a review after Lipscomb got the Nobel Prize. He said, boranes are not electron deficient, but chemists are theory deficient. In other words, B6H10 has all the electrons that it requires. B6H6 2- has all the electrons that it requires. But we had always felt B2H6 is electron deficient. It is because we grew up with C2H6. Ethane we grew up with, and 2 electrons less. I mean, I would say, a student who learned the boron chemistry and B2H6 initially and assumes that yes, B2H6 is electron sufficient and it has two bridging hydrogens, would be forced to say that, oh, C2H6 is electron excess and it has no choice but to remove the bridging. I hope
Yeah, I got it. Thank you. Yeah. Okay. And then perhaps actually with the permission from the chair, actually, I just want to state one fact about Professor Jemis. Professor Jemis, he worked with two Nobel laureates, Professor Roald Hoffmann for I think 2 or 3 years, and later worked with the great Professor John Popple, another Nobel laureate, and his mentor, of course, the long-standing relationship he has with the Professor Clare. Actually, Professor Clare actually produced, I think, more than 2,000 papers, if I remember right. Actually,
so
he worked with. Yeah.
I wanted to say that I was pleasantly surprised to see Jing Li.
Yeah,
worked with Professor Roald Hoffmann.
I know. Yes, exactly.
About 30 years after I did.
Yeah, and something about Jing Li. She did actually theoretical work to Professor Roald Hoffmann,
right.
And actually went to entirely to experiment. Actually, now what she has talked about is a pure experiment. And I asked her actually why actually that. She said actually she did postdoc with another person in Cornell and then learned the whole thing. And then, of course, she does some computational work, theoretical work too. But a great experimental chemist now, at least.
I mean, I'm an experimentalist, even though I don't do any experiments.
Yeah. Okay. No. Thank you very much, Professor Jemis. Time.
Thank you, Professor Padmanabhan. Thank you, Professor Jemis.
Thank you.
For a wonderful talk. So we'll, I think, move to the next talk.
So may I share that slides, Naveen?
Yes, sir. Yes, sir. Our next speaker of the day is Dr. K.V. Radhakrishnan.
Share the slides.
Yes, sir. Yeah, you can go ahead. Next speaker is Dr. K.V. Radhakrishnan from CSIR NIST Trivandrum. I request Dr. Zeena Pillai to give the brief introduction about Dr. KVR.
Namshivaya, I hope I'm audible to all. Good morning, everyone. It's a great privilege for me to introduce Dr. K.V. Radhakrishnan. He's a senior principal scientist and head organic chemistry division NIST Trivandrum. He received his early education from Christ College, University of Calicut. He completed his PhD in synthetic organic chemistry from the University of Kerala under the supervision of Dr. Vijay Nair. Subsequently, he held postdoctoral positions at Tohoku University with Professor Yoshinori Yamamoto, Molecumetics Institute with Professor Michael Kahn, and NPG Research Institute USA with Professor Bert Fraser-Reed. His research interests include the development of novel synthetic methodologies utilizing pentafulvenes as synthons, synthetic carbohydrate chemistry, and palladium-catalyzed organic transformations towards pharmaceutically important molecules. His research interests also include tapping the potential of bioactive molecules from the plants of Western Ghats. He has authored more than 100 research articles and has got several book chapters and patents to his credit. One of his most recent ACS publication is it's a very interesting article which combines photochemistry with biosynthesis. It's basically the photochemistry induced biosynthesis of terpenoids. He has received several awards. Just to name a few, he's a recipient of CRSI Bronze Medal in Chemistry in 2016, Mesaka UAE Excellence Award in 2015 for outstanding contributions in the field of science for inspiring the young generation. I must also mention here that he has also done his Master's in Human Resource Management from University of Kerala, and that too with a first rank. In addition to all his achievements, he's also an active member in a number of collaborative projects based on functional organic materials, photovoltaic devices, and optical switches. It's a great honor for us to have you here, sir. Over to Professor Radhakrishnan. Thank you.
Thank you, Sina. So can all of you see my slides?
Yes, sir. If you can put it into a slideshow mode.
Okay. First of all, let me thank Dr. Padmanabhan and Dr. Naveen for inviting me for this one, for this talk. especially I'm going to talk to you right now something different from what you have been listening so far. You had phosphors first, and then followed by the theoretical chemistry by Professor Jemmis. And now I am going to take you to the flora and fauna around. So the beautiful nature. So I will just take you through just to motivate youngsters and the young colleagues to the wonders of flora and fauna around us. And I have titled it as bioprospecting of medicinal plants used in herbal formulations. And you know why the herbal formulation is important, and all those I will come to it one by one. So at the outset, I would like to dedicate my talk to my dear boss, my third postdoc supervisor, with whom I did my postdoc in the area of synthetic carbonate chemistry, Dr. Bert Fraser-Reed. In fact, this was one of the most successful and enjoyable time in my career by working with Dr. Bert Fraser-Reed. He passed away on 25th May 2020. And he was our boss. And boss is only a term, and we were his rowdies, Fraser-Reed's rowdies. So with this dedication, I would like to get into what I am and our group is doing. So I am basically a synthetic organic chemist, wherein we are working on process chemistry, where we are developing processes for advanced pharmaceutical ingredients, crop protection chemicals, etc., where our role is utilizing our synthetic expertise for troubleshooting and also impurity profiling of APIs, etc., which is the major project. And these are the major projects in our division. Funding comes from that. In addition to that, being an organic chemist, I am involved in synthetic methodology development, mainly the green synthetic methodologies, homogeneous catalysis, and also synthetic carbonate chemistry. And the last one, which I am going to talk to you about today, is the phytochemistry and herbal formulations, which is a recent activity in the last 5 years, which we are taking up. This is a passionate activity. So while coming to the herbal formulations, all of you know now we are facing the horrific pandemic of coronavirus. And also in the 21st century, we have witnessed several coronavirus infections and so on, like starting from the SARS virus in 2002, and then going on to the MERS virus, Ebola, and so many. Not only viruses, and we are also facing another problem of multi-drug resistant strains of bacteria. Most of the antibiotics which we are using now is no longer effective for several of these bacteria because they have mutated, they have become multi-drug resistant. So in fact, when it comes to herbal formulations or Ayurvedic formulations or the traditional treatment strategies, it is mostly on prevention of these diseases, and mitigation also comes into it. So if you take Ayurveda, there are different types of herbal formulations, starting from the water-based decoctions called kashayams, and you can have the powders like churnam and the tablets, and also the lehium, which is just like it's a semi-solid for immunity boosting. Most of them are immunity boosting. So I have listed several of them, which is mainly used against infectious diseases, and I am not going to add details of these things. I will just take you to some of them. Usually in infections, when you have a bacterial infection or a fever or a viral infection, you have the fever. So depending on the type of fever, you take different types of formulations. You cannot take the same type of formulations of all fever. So you have to look at the different types of symptoms. For example, a simple polyherbal formulation with 3 ingredients is Amrutottaram Kashaya or decoction, water decoction. And you can see the second one is the Tinospora cordifolia. In Malayalam, it is called Chittamrudu. And you have the ginger also, and another Harideki, which is called Terminalia Chebula. Like that, there are many other kashayams or the decoctions which are used. And when you go through the Barangyadi Kashayam, this is mainly used for fever associated with respiratory diseases. And another one, the fever associated with the chest infection and so on, Ulichadi Kashayam and Pajanamridam Kashayam, etc. I just taking you through the Ayurveda, different type of Ayurvedic medicines. In all these medicines, you can see there are different types of herbs. And in my talk, I will be taking you through some of the herbs and how it is getting active. So not only in the prevention. In the prevention and mitigation of infectious diseases, we are not just talking about antiviral or antibacterial. So we have to stop the entry of pathogens into our body. Which means you have to have more immunity. So I will talk about both of it in terms of some of the common plants around us and how it is boosting your immunity, how it is preventing the entry of pathogens to our body. So the phytochemistry and herbal formulation is not a single man army. This is actually an army, real army, which is a multidisciplinary activity at the chemistry-biology interface with a number of collaborators. You need biology people, taxonomists, and so I mean Ayurveda people, etc. You can see there are several number of collaborating institutes involved in it. So it is a multidisciplinary activity, starting from folklore healers, sociology, cancer biology, etc. So over the last 5 years, we have the expertise in phytochemicals and the microbial natural products, which is a focused activity right now, wherein we have screened around 125 species of medicinal plants from 45 families, isolating compounds with wonderful structures. As an organic chemist, I always get excited with these structures with several chiral centers and also the characterization. So we have the expertise in isolation and identification of microbial natural products as well. And these are being utilized in developing protocols for the standardization of herbal products, and also the facility. We have the facility for herbal product formulations, utilizing the biological platforms available. So these are, I am not going to the botany part of it, as I told you, because this is a chemistry audience. There are around 45 families and 125 species of plants already we have. So let us come to one family. This family is called Menispermaceae family. It is nothing but the family of Amrud. Amrud, you know, in Amrud means, which gives you life. Okay. So this family of plants is mainly used in different infections like asthma, tuberculosis, dysentery, and so on. So let us go to one by one. So if you look at these plants, you can see Tinospora cordifolia is the chittamrita, and there are many other plants in the same family. I will take you to one by one. So this family is very important. Right now, in the context of COVID-19 infections and viral diseases, this family is very important because one of the plant from this family, which is called Coculus hirsutus, in Malayalam it is called Garida Kodi. This is under clinical trial in India against COVID-19 infection, along with 3 other plants which are commonly found around in Western Ghats. So we are really fortunate to have the Western Ghats, which is the hottest, one of the 8 hottest hotspots of the biodiversity in the world. So if you go to the Tinospora cordifolia, this is the Chittamrita. Amrita, so this is used in different formulations which are used in infectious diseases. So in this family, Menispermaceae family, the most important thing to note, there are different types of natural products starting from flavonoids and all. But the major one on all these plants is the alkaloids, several types of alkaloids, and mainly the berberine alkaloids. So as you can see in these slides, Tinospora cordifolia, it's a climber. It's a climber, and you can see the different types of flavonoids like naringenin, and also it has several steroid compounds. These are the major compound in this plant called the maquisterone. which may be, I don't know, it's usually in herbal formulation, it is the synergistic activity which is playing the major role, magisterone. And there are several other compounds in it. And there is another exotic plant in Western Ghats right now. This is an exotic plant called Tinospora crispa, and that can be distinguished from the original Tinospora cordifolia because you can see the thorny structures on the stem. Tinospora crispa is an adulterant, which is used as an adulterant in place of Tinospora cordifolia. And this plant is really toxic. Though some of the compounds are really good as anti-diabetic, but as all of you know, dose determines the toxicity. You are not supposed to take any herbal without a doctor's prescription because these are dangerous to our liver and kidney and so on. So this is while working on any family, we work on all species in the same family. All species available in Western Ghats in the same family. And another plant which I want to take you through is from the same family is the Cocinium fenestratum. Cocinium fenestratum is also known as Maramanjal in Malayalam, or you can say it's tree turmeric. Okay, wooden turmeric. Because when you cut the stems, which is a liana, this plant is a liana and a climber. When you cut the plant, you can see yellow color. And because that yellow color is due to an alkaloid called berberin, which is present in very good amount. For example, 0.1% of that dry weight is the berberin. And you can have many other alkaloids as well. And just like in any other Menispermaceae family, it has steroids as well, like magisterone, etc. And this is used in, this is an endangered plant right now because it takes almost 15 years for the plant to flower and have the fruits, I mean the seeds. But before it is 15 years, people were cutting it, and then it is now ready in the red list, and I think the forest department is planting more of it. So this is used in severe infections, especially of the eye infections, which follows many viral diseases. There is another plant called Tilacora acuminata. This Tilacora acuminata, as you know, this in Malayalam it is called Vallikanjara. This is used in folklore medicine, though this is in the same way, mainly in snake poison treatment by folklore healers. And it is really good, really wonderful, because you look at these molecules. These molecules are cyclic alkaloids, where you can see this nortilacorin, phoscolin, and tilacorin, etc. And right now, all over the world, people are trying to repurpose molecules for COVID-19, repurpose already available drugs against COVID-19. And one of these molecule called, one of the similar molecule called tetrandrin from the same plant is now being in clinical trial in Brazil for COVID-19. So I just want to take your attention to the wonderful compounds in the herbal formulations, which may be antiviral or entry-level inhibitors of viruses or any other infections. And then go to another plant, which is widely used in Ayurveda. This plant is called Cyclia peltata, or another name in Sanskrit, it is called the Rajapata. It is a pata plant. And this plant is, this plant is really interesting because you take the leaves of this plant, make a paste and put some water in it. After some time, it becomes a gel, hydrogel. Okay, and many other plants in the same family has that property. You might have seen some videos circulating on, the Jalastampini and all those things. It is not Jalastampini. The compounds in that plant makes a hydrogel. Forms a gel. And another plant, Cocculus hirsutus, also forms a very good hydrogel when you mix it with water. So you can look at this molecule. We still have many molecules to be identified because the structural characterization is very tough in this case. And now these are all these molecules. So while working on these plants, one thing you have to notice is phytochemistry is being practiced all over the world. But in India also, some people are doing phytochemistry. But in the last 20, after 75 or 80s, I would like to say that people stopped working in the area of phytochemistry because it is laborious. You have to take a large quantity of plant material and then extract it, then purify the compounds, then then whether it is a non-compound or unknown compound, you have to characterize it first, which is actually very tough. You need to have a teamwork to do this. And also, after doing all those things, if you try to publish these things, it is very difficult to publish because you can publish. But when you are focusing on the impact factor of the journal, it is very tough to publish in high impact journals. But it is very useful work as far as the society is concerned. So what I was talking to you about, a family called Menispermatia, and this family is the family of Amrud, Chitramrud, which has several alkaloids, several plants having alkaloids, and there are, and whatever I am talking to you is about the plants which we have studied, which I know very well. So, and these plants and its compounds are, from these plants are in clinical trial against COVID-19 in different parts of the world, and in India, the Cocculus hirsutus. So it is not just taking an antiviral formulation. You have to boost your immunity. How do you boost your immunity? So during COVID-19, you may be listening that, I mean, you have to take food which boosts your immunity. You take more fruits, you take more antioxidant stuff and like that. So that means you have to be very, very particular about the food which you eat during the type of during the time of pandemic. So all of you may be familiar with this one. I hope so. This is the biggest fruit, jackfruit, and jackfruit is one of the best to boost your immunity. So not only jackfruit, there are many other plants in this family which boost our immunity. And how it is boosting your immunity, that is what I want to tell you about. I mean the jackfruit family plants, how it will boost immunity and how it will prevent, how it is, why it is antioxidant. So in the jackfruit family, some of my colleagues in my age may be remembering this fruit. This is called Artocarpus hirsutus, which is another, otherwise it is called Artocarpus hirsutus or Anili. In some places it is called Aini. It's a very delicious fruit with a little bit sour color. So you look at this, from the bark of this tree, we were able to isolate several natural products. You can see these are all flavonoids. And you can see these flavonoids has a lot of phenolic groups and also the prenyl groups. So the prenyl groups and these phenolic groups are radical scavengers. So that is why it is called, these are antioxidants. In addition to that, the jackfruit family, all jackfruit family plants is having tetrahydroxystilbene or oxyresveratrol as the main compound. So that is what it gives the antioxidant activity. And you see the wonderful compounds which we isolated, artocarpine, cutraflavone, all are prenyl flavonoids, and also you have geranyl flavonoids which can act as a very good radical scavengers. And each molecule will be having its own chemomarkers. Each species will be having chemomarker. In the case of Artocarpus hirsutus, it is the methyl substituted oxyresveratrol which is the chemomarker. And there are many other plants from the same family. Some of you may be familiar with this. This is a unique plant called Artocarpus camansi. And you can see the compounds in it. So the major compound is always oxyresveratrol. But along with that, we have another artonin, artocarpacin, and like that several compounds in the same plant. And when you go to the northern Kerala part, you can see that they are using the fruit of an Artocarpus family plant called Artocarpus lecucha. This lecucha is really a sour in taste because it has a lot of oxoresveratrol. It is called pulinjaka or monkey jackfruit, which is a threatened species. And this is a storehouse of oxoresveratrol. And from Kerala, this oxoresveratrol is being exported to many different countries because the oxoresveratrol is one of the main components in the face. The whitening creams. Oxoresveratrol. Always there will be 0.02% of oxoresveratrol in these cosmetic creams. And the hardwood of this plant is having around 9.2 gram from 1 kilogram of 9.2% of oxoresveratrol. That means 1 kilogram gives 46 gram of it. So when you come to this plant, this is the prenatal oxoresveratrol, which is the chemo marker for this compound. So and then this plant, you may be familiar with this plant. This plant is known as Shimachaka or Kadachaka, Artocarpus actilis. And this is used as a vegetable in Kerala. And even the fruit, you can dry it and powder it and use as a dough along with your atta. So look at this. This is also having similar derivatives of flavonoids. And when it comes to the Kadachaka, you can see it is a geranyl. You can see the red structure. This is the chemo marker for this. So I can go on telling like this. And in the same family of Moraceae family, there is a number of other species of ficus, areal like that, Nalpamarum, which is used in skin infections and skin problems. And the Nalpamarum is the 4 plants called Ficus racemosa, Ficus microcarpa, megalensis, and religiosa, which is used in several herbal formulations for skin ailments and skin health. So all these molecules, the plants are having resveratrol and oxoresveratrol derivatives. Then I will take you to another family called the Myristicaceae family. Myristicaceae is the family of nutmeg. Nutmeg, all of you know, nutmeg is used as a very good spice because it's a storehouse of many phytochemicals. When you look at this Myristica fragrance of the normal nutmeg, you can see that in Kerala we use the fruit rind and the maize and the seed. The maize and the seed is used in number of Ayurvedic formulations. And the maize is a storehouse with hundreds of compounds in the maize. So when you have so many compounds, purification is really a trouble. You can see we were able to get around 30 compounds only because the purification and characterization is a pain. But along with Myristica fragrance, in Western Ghats you can see several other species. One such species is Myristica malabarica, and it looks similar, and seeds are similar, and the maize color may be different, but the problem is it is totally different molecules. The molecules in this Myristica malabarica, it is the nutmeg family, but the nut is not so good. It is really toxic. While working on it, many of my students got allergy, and it has the main compound as malabaricons, which is a phenolic compound with a long chain in between. And when you go to the swamp areas in Western Ghats, there is a swamp areas which is called Myristica swamps, Jadikya Chaduppugal in Malayalam. And this is a long nutmeg. And there also, and you can see the plant, since it is in the swamp, you can see the roots from the stem like a hanging. So it has unique compounds. Along with the malabaricons, it has unique compounds called dactyloidins, and which are now under evaluation against several biological targets in our lab. So there is another one called Myristica bedomi. Myristica bedomi is also having similar morphological features for the fruit and fruit rind, but the compounds are different. So what I want to tell you is, so the nutmeg which we can use is only the Myristica fragrance, the normal nutmeg. all other nutmeg which you may see around, because we are part of the Western Ghats. So we may have these plants in our land, or when you go to the forest, and also you can see, but even by mistake, you should never eat it or take it, because it is highly allergic to many people. So, so there is another family called a Nyctanginaceae. This is the family of bougainvillea. Bougainvillea plant you may know. And in the bougainvillea family, there is a famous plant. In Malayalam, it is called Nalimani Puvu or 4 o'clock plant. So, and when you take the look at the Nalimani Puvu, you might have seen the seeds of it, but it has a very good rhizome. The rhizome is almost like a tapioca or a kappa. That is a very good medicine for burn healing. This the rhizomes of Mirabilis jalapa or Nalimani Puvu. You look at these molecules. The red molecules are the molecules which you isolate. These are all novel molecules. These are called rotenoids. And you can see different types of rotenoids. And these are some of the things which we did recently. I will not be going to the biology part of it. And I want to take you to another family called Delineaceae. Delineae indica, one famous plant which you can see in both in Eastern Ghats and Western Ghats is Delineae indica. This is also known as elephant apple, because elephant is very much fond of this fruit, because it is sour in taste. And if you go to IIT Guwahati campus, you can see this fruit all over, this plant all over the campus. So we have isolated several molecules from it, mainly the betulinic acid and another wonderful compound called palmaromycin. You look at the structure of palmaromycin. So these are a class of compounds called presumerins, deoxypresumerins, and the palmaromycin JC1 is this pyrocyclic compound. And when we collected the plant material from Assam, we got this particular compound, which is already reported in some fungus. So we are just looking at how this plant is having this type of thing. So plants are producing phytochemicals to fight against infections. So according to the geography and the soil conditions, the phytochemicals in plant changes geographically and seasonally. So in Western Ghats of Kerala also we have another plant called Delineae pendagyna, which is called, you can see it. And if you go to Isert Trivandrum, you can see when you get into Isert Trivandrum, on both sides you can see this tree in plenty, and the fruit is edible, which is used in in folklore. It is used for easy delivery for women, and also for several infections. And all of you are familiar with Meliaceae family, the family of neem. And there are many other plants, many other than neem in this family. This is called chemmaram or Aphanemyxis polystachya. In Sanskrit, it is called Amura rohituga. Amura rohituga is mainly used in herbal formulations for treating splenomegaly, the enlargement of spleen. So look at these molecules. So all these molecules are reported from some other species from the same family or some other family. So but the molecules are wonderful. All these are, whether it is known or unknown, doesn't matter, because the biology part of it is not known. That is what we are really looking at. And also even non-molecules, we are taking it forward for further functionalizations and so on. Semi-synthetic modification, so that we can have very active molecules. And look at this. This is another plant called Cipitasa basifera from the family of neems. If you go to Ponmudi, you can see this plant all over. And this Cipitasa basifera is used in folklore remedies mainly against viral infections. Cipitasa basifera. You look at this complexity of these molecules, really complex, and that complexity gives you challenges, and that is really exciting when you go for the structural characterization. So you have highly oxygenated molecules. These molecules are known as limenoids. So like that, there are several plants. And if you go to another family called Samarubiaceae family, there is a plant called Samadera indica. If you come to NIST Trivandrum campus, you can see it, because we have planted it all over, because it is a very precious plant. So it is used against rheumatoid arthritis, in the severe form of rheumatoid arthritis with inflammations. In Malayalam, it is called Amavadam. So you look at this molecule. This is called the core structures which you see in this slide is known as the cosinoids. These cosinoids are very much bitter in taste. When you are doing the column, you can feel the bitterness in your lips. So that much bitter, but it is very very good for external applications, and several of them you can isolate different types of cosinoids called samadarins, etc. From samaderin A, B, C, and these are all stereoisomers. So when you have this stereoisomers of the same molecule, characterization is a very challenging and exciting for organic chemists or whoever likes NMR spectroscopy. And there are several plants in the same family. This you may be familiar with. This is used as in all over Kerala. This is the wood of it is used in making matchsticks and matchbox. It's called Tipetimaram or Peruvalam. And you look at the molecule in it, so nice. So this, in fact, there are several new molecules and unknown molecules as well. So these are all anti-inflammatory. When you come to the Samadera family, Poaceae indica and all, these are all anti-inflammatory molecules. So once we isolate these molecules, once we take the extracts, we go for this biological screening against several anti-inflammatory targets like NF-kappa, BT, NF-alpha, etc. So not only that, we have several other herbal formulations, not only against infections. Right now, we have another problem because we have the huge population of geriatric population. So when you have more and more geriatric population, you come across several CNS disorders, central nervous system disorders. As you may be aware of it, Alzheimer's, Parkinson, dementia, and several types of memory disorders. In Ayurveda, there is a family called the Celastraceae family, and the traditional use of these plants are in memory enhancing, and also some of them are used in anti-diabetic also. This is a plant which is used as a single plant remedy for memory enhancing and also for hyperactive children and all. But you are not supposed to go and take it as such because you have to take under medical supervision only as per the advice of a doctor. So the seed oil is being used. So look at this. This is called the Celastrus paniculatus, and this is called Celastrus paniculatus. In Malayalam, it is called Kilidinipanji. In Sanskrit, it is called Jyotishmati. Jyotishmati. So Jyotishmati is one of the main component of Medhya Rasayana. Medhya Rasayana means the brain, the Rasayana, the herbal formulations which is used to stimulate the brain. Okay, so when you come to the chemistry of that, that is more exciting. When you come to the molecules in this seed oil, in the seed, you see the structure. You have 2 cyclohexane rings and a furan ring. So when you have this type of skeleton, this skeleton is called agarofuran. So we were able to isolate around 12 molecules from this plant. This is already reported in 1970s. But when we collected from the northern Kerala, Wayanad area, we were able to get 3 more new. And you can see, as you can see here, the difference between all these molecules, the 12 molecules, is in the stereochemistry in the cyclohexane ring, the substituents in the cyclohexane ring, and the derivatives. So we all 12 compounds we were able to establish the structure with the aid of 2D NMR spectroscopy, and some of them we were fortunate to have very good crystals. If you are not able to do it with 2D NMR, and we will have no clue in some cases because almost all molecules, some of them will be like a glue. You have no idea what it is. Sometimes it takes months to characterize the molecule. So by doing so, what we are learning actually. So I don't have time to go through each and every plant. It will be boring for you also. So by working on several species of medicinal plants, around 125, we were able to get the huge repository of around 450 natural product phytomolecules, which are then taken up for biological evaluation. And one of the biological evaluation we are really involved in is in the antimicrobial resistance against multi-drug resistant strains of bacteria. As you know, nowadays you may be aware of superbugs. Superbugs are nothing but, for example, Staph aureus. If you take Staphylococcus aureus infection, you have that bacteria all around. But when you get infection from the hospital, that is deadly because it is resistant to most of the antibiotics available in the market. And so what we will do then? We had to go for new antibiotics, but the companies are no more interested in developing new antibiotics because within 2 years of its the discovery, the bacteria will become resistant to it. So we have screened several of them. When we screened around 350 phytomolecules against MDR strain, we are fortunate enough to get 3 molecules which are very good, active against Staph aureus, which is almost equivalent in activity, just like the vancomycin, which is the antibiotic used against multi-drug resistant strains. And in addition to that, what we found is these are all showing very good synergistic activity with existing antibiotics. As you may know, earlier we were taking a ciprofloxacin or amoxicillin antibiotic. Now, when you get infections, doctors are prescribing augmentin, which is a mixture of 2 antibiotics. So this is a 3 advanced hits in this line. And also, as you can see here, the way forward is developing these hits into the drug lead. So there, our organic chemistry expertise is very much needed because we cannot depend solely on plants to make it. So we are developing the process for these molecules, which we have shown. In addition, since these molecules are showing very good, the MDR antibiotic activity, we have already developed the topical antibiotic creams against multi-drug resistant strains, which are now under animal studies in skin models at CSIR CDR. So as I told you that I am basically an organic chemist, so I cannot stop my urge for doing organic chemistry. So along with the process chemistry, when I see these molecules from plants, I really get excited. One such plant is shown here. You can see this is called Zingiber cerumbet plant, is the Zingiberaceae family. And this plant is a rich source of the humulines and cerumbon, which is a sesquiterpenoid, humulene sesquiterpenoid. And if you take 1 kilogram of the plant, you get around 40 gram of, 1 kilogram dry weight, you get 40 gram of cerumbon. So you can do wonderful chemistry with it. You look at the structure of it. So we were thinking, how can we do the transalveolar cyclization of these double bonds? When you look at the conformation, you can see you can do that actually. Can we do transalveolar cyclization? And we did it. So what we did is with very simple chemistry, green chemistry, by just changing the Lewis acids and the different additives in the reaction without any complex step. In single step, you can transform into several natural scaffolds. Like you can have 8 5-fuse ring systems, 7 5-fuse ring systems, and so on. And when you have different types of substitution, you get different type of natural scaffolds. These are all published, I think, in 2018. And you can functionalize the cerumbon very easily. You can do an oxidation. You can have a aldehyde group over there. You can have a epoxide group over there. You can functionalize it in several ways. When you functionalize it, that leads to very interesting scaffolds, which can be utilized in the total synthesis or any other target-oriented synthesis of molecules. So this is a recent result wherein we were able to, mimic a biomimetic route of the synthesis of of oxo-bicyclo-3,2,1-octane motif. So this reaction is very simple in the sense you have serum bond, and this one you see the stereochemistry of the double bonds in serum bond. All are in the same configuration. When you irradiate with light, you just put it in sunlight. So it undergoes isomerization of the double bonds, and when it isomerizes in presence of a Lewis acid, the Lewis acid generates carbocation. So it is nothing but organic photochemistry combined with the chemistry of carbocation. It's a quantitative reaction. So we're not using any toxic chemicals or anything. You just put it in light and use your imagination. This is now in organic letters ASAP. I think last week it is in the thing. So you look at this. So the first one is serum bond, and which undergoes isomerization. And after isomerization, it is just going to different types of cyclization, formation of carbocation. I'm not going to the mechanism. So the structural characterization of these molecules was really a pain. We took 6 months because there was no precedence for this type of reaction. This biomimetic, this type of cyclization, there was no precedence. So what we did is we took it forward in functionalize these molecules, and we did several transformations of the product to see what type of structure it is. So that in fact led to a number of different cores. So utilizing the transformation, you can get different types of natural products cores. So, and I cannot stop the presentation without telling about the carbohydrate chemistry, because that is an exciting area for me and the passion. And when you isolate any, the natural product molecule, you come across several of them polyhydroxy molecules. And when you isolate it, the carbohydrate part cleaves off. So, right, and a program in our group is looking at how we can reconnect this carbohydrate. It is not so easy to reconnect the carbohydrate to the same position. You have to develop methodologies for regioselective and stereoselective glycosylations. So that is what we are working on right now. So I was talking about the herbal formulations and the local health, traditional health traditions. But this the traditional knowledge and the local health traditions is facing a crisis. The root cause of the crisis is the loss of knowledge base relating to the raw drugs. Relating to the flora and fauna around us. Right now, we are responsible for it. Actually, the present generation, the current younger generation, is not aware of the beauty of the plants and the richness of the plants around us. And this knowledge erosion is really happening faster than the resource erosion. In fact, these are locally available low input technology, which can provide useful hints for future technological development. So, as I mentioned to you in the beginning, this is not a single man army. We have to start with folklore healers, tribal healers, wherein you have to be one among them. You cannot do the research just in the lab. You have to interact with the society, mingle with people in the society. They are the knowledge holders. So they are the knowledge holders. The tribal healers, the traditional healers are the knowledge holders. And only when you are one among them, you can do better. So you have to get into the society to do such type of, the interdisciplinary research. So this is all possible with folklore healers, traditional healers, like that. So the PhD students, I would like to thank my PhD student, project assistant, MSc student, number of MSc students, and the MD Ayurveda students. My group is, our group is actually a mixture of biology PhD students and chemistry PhD students. So since there was a delay in getting the biology screening, we thought of having our own screening facility. We recruited the postdocs in the biology, like cancer biology and many other areas. And then with their help, we have all screening facilities established in our lab. And that is how we go on. So when we do research, we can do the research like the one which I have shown here. You can go after the basic science problems or whatever it is. It will be exciting. You can publish good papers and you can get excited about H-index citations and all those things. That is cool, really cool. But when you are together, you can do wonders. When you are together, you can do wonders. So for working on problems which can go directly to the society, we have to work together and go together as a dynamic team. That is the most important thing as far as this type of work is concerned, phytochemistry. I think that is true for any type of work where a translation is required. Translation of our basic science to the society is required. So it is raining all over. So, since because of Corona, we are not able to enjoy the rain so much. It is threatening also because we have landslides all over taking the lives. But even then, and thank you for your patient hearing. Thank you.
Thank you, Dr. Radhakrishnan, for your very informative talk about the herbal formulations and also for showing us the wonderful organic chemistry you're doing in your lab. So I remember you mentioned you have a meeting just after this. Do you have time for a couple of questions?
Yes, I have.
Okay. Yeah, I think we can take a couple of questions. If anybody...
Can I stop sharing?
Yes, sir. Yeah. Okay. Maybe you can turn on the video so that we can see.
Hello. Any questions? I hope. Padmanabhan sir. Okay.
Yeah, I see Padmanabhan sir.
Sir, I cannot hear you.
Am I audible?
Louder.
Am I audible?
Yes, yes. Yes.
Okay. Thank you so much, sharing with us, the exciting molecules separate from the natural, plants, and also the conversion you do actually. So I just want to comment on your work actually. I know that you are a basic organic chemist, and you took up on the task of isolating molecules from the plant, and normally a phytochemist actually just isolate them and that's it, characterize and leave it. And really exciting that you take those molecules and convert them in a very easy and facile manner. For example, the conversion of serum bond, am I right? Serum bond to your other product by easy irradiation, sunlight irradiation, and said it's a quantitative conversion. In that connection, I want to actually, serum bond, I saw the plant you talked about. Is that a fruit? Did you get that about 40 grams? 40, you said you got 40 grams of your serum bond from.
It is called the Malenji or cartin.
Oh, okay. Is that a fruit? We see that.
No, we take the rhizome of Inji.
Oh, okay. And regarding the jackfruit, it's very interesting. Is the molecules you talked about? Did you isolate them from the fruit or from the bark or a?
From the bark and the fruit.
Oh, bark, not the fruit. I mean, you.
From the bark and from the hardwood.
Okay. Great. Thank you so much, and for sharing us, your wonderful work. And what is exciting about your work, actually, that you reached out to the interior part of Kerala, actually, where the tribal people live. And as you mentioned, that it's very important for us to really act immediately and go to them and then get the information from them, because slowly dying out, actually, and they have so much knowledge in store about the plants and their actions. And I'm so happy that you took all the pains to go there and then collect the plants and talk to them, of course, and get information. And then thank you for sharing that information with us.
Thank you, sir. Thank you for inviting me. And I hope I did not bore all of you with my botany.
So, exciting. I am sure actually all of us really appreciate and then, really, enjoyed our talk very much. I'm sure actually.
Any more?
I think it was very informative, and I think most of our youngsters would be kind of encouraged to start working in this particular area of research. So are there any more questions? If not, then let's all thank Dr. Radhakrishnan for this wonderful talk.
Thank you, Naveen. Thank you, Navan sir. Thank you, Sina, and all faculty members of Amrita University, and also other, the other speakers for this particular seminar. Thank you very much.
You are welcome, and also we would like to visit us and then give a talk actually in person after all this COVID.
Okay,
yeah, hopefully.
There are a lot of things to do in this area actually.
Okay,
because
I know. Actually. Thank you so much. Yeah.
Thank you, sir.
Okay, I think this is the time to go to our fourth speaker of the day. We have Professor Bais Martinsi from Durban, South Africa, joining us. Professor Martinsi, I see you are online. Can you turn on the camera, please?
Yes, I have. Hello.
Okay, I think. Yes. So I request Ms. Divya to introduce Professor Martinsi to our audience.
Good morning, one and all. It's my honor to introduce Professor Bais Martinsi to all of you. Professor Bais Martinsi is a renowned physical chemist in the School of Chemistry and Physics at University of KwaZulu-Natal, South Africa. Her research expertise lies in the areas of photochemistry, solution thermodynamics, and environmental chemistry. She is a well-versed academic and has held visiting professorships at West Virginia University, the University of Wales in Cardiff, Portland State University, and Geetham University. Professor Bais has enormous number of publications and citations in high-impact journals. In 2011, she was awarded the university's Distinguished Teacher Award. She has served as the president of South African Chemical Institute, SACI. She is a fellow of SACI, the Royal Society of Chemistry, and IUPAC. She has been elected as a member of the Academy of Science of South Africa. Today, we are highly fortunate to have Professor Bais here for ICMSE 2020. The title of her today's presentation is Nanotechnology for Wastewater Treatment. On behalf of ICMSE 2020, I invite Professor Bais to deliver her talk. Thank you.
Thank you very much for that kind introduction. And thank you very much to the organizers for inviting me, and especially to Dr. Kulkarni for his extreme efficiency and attentiveness to all the details. So it's my great pleasure to be able to speak to you today. Before I start on my technical talk on the use of nanotechnology for wastewater remediation, I'd like to tell you a little bit about where I come from, because there are many parallels with India. And in this COVID situation, we can't travel. So at least I'd like to show you a little bit about the city where I live in. Well, I live in South Africa, which, as you know, is right at the southernmost tip of Africa. These are the 9 provinces of the country. And I live in KwaZulu-Natal, which was formerly known as Natal. I live in Durban, which is on the sea, on the border of the Indian Ocean, which you also share, but the capital of the province is 90 kilometers inland in a place called Pietermaritzburg. Now, Durban is the busiest harbor on the African continent, and here you see the harbor with all the ships, and here we have the Indian Ocean, and this is the city center. Now, just like India, we were also a British colony. So our city hall in Durban is a complete replica of the city hall in Belfast in Northern Ireland. This is our beachfront, where you see the Indian Ocean. This is known as the Golden Mile. And this is all the hotels along the Indian Ocean side. And this is the harbor with this very nice Victorian rail, which has remained. Now, the main black population in the province are the Zulus, the Zulu-speaking people, which are very well known for their beehive huts and their beautiful beadwork, as you see here. But Durban is also has the biggest population of people of Indian descent outside of India. They came to South Africa in 1860 to work in the sugarcane fields. So in Durban, you will find many beautiful temples. We have the biggest mosque in the Southern Hemisphere. We have an Indian market which sells wonderful spices with humorous names like Atomic Bomb and Mother-in-Law Exterminator. And we have devised our own form of food called a bunny chow. It's half a loaf of bread where the inside has been scooped out, and you fill it with curry, and then the piece of bread that you took out forms the lid. This was devised so workers could take their lunch to the fields in the times when we didn't have plastic containers. The capital is very colonial, very British, and it has beautiful red brick Victorian buildings, as you see here. But it is famous because this is where Gandhi was thrown off the train and where he came to his realization of passive resistance. So now we commemorate that. We have a statue of Mahatma Gandhi outside the railway station in the capital, Pietermaritzburg. I work at what is known as the University of KwaZulu-Natal, which in 2004 was formed by the merger of two previous universities, the University of Natal and the University of Durban-Westville. We have some 55,000 students spread over 5 campuses, and I work at what is known as the Westville campus, and here you see our chemistry building where the work that I will describe today was carried out. So let me now go to my technical talk. We are all very well aware that worldwide we have a deterioration of our water quality, and this water quality scarcity poses a real threat to human activity. We therefore need much more improved water purification technologies, especially to remove what we now see are emerging contaminants in our water. And currently we have 2 main technologies that we use to remove these pollutants. They are phase separation techniques such as adsorption for pollutant removal or advanced oxidation processes for pollutant destruction. Now, nanotechnology can play an important role in resolving these water purification and quality issues because the advanced materials that we can prepare can enable greater water reuse, recycling, or desalination. The materials that nanotechnology enables us to make have strong adsorption, redox, or photocatalytic properties that allow us to use them to treat contaminated water. However, we need to be sure we meet certain conditions, such as environmental security, that the materials we use are able to be reused and don't create a secondary pollution problem, that they are of low cost and high treatment efficiency. Now, as we know, nanomaterials have at least one dimension in the nanoscale from 1 to 100 nanometers. This small size enhances them with different physical, chemical, and biological properties to their bulk size equivalents. And this arises because of the higher surface area to particle size ratio, and therefore they are enhanced with different optical, electrical, and magnetic properties. And we can exploit these different functionalities to create new adsorbents and photocatalysts. And so we can develop these nanomaterials to be better materials for decontaminating our water sources. So the aim of the work that I will present today was to prepare nanomaterial containing adsorbents for the removal of heavy metal ions or organics, or photocatalysts for the destruction and mineralization of organics. In these materials, we incorporated either carbon nanotubes or other carbon materials and nanoparticulate iron oxides. So let me first look at the adsorbents that we have made and tested. Now, adsorption has certain advantages because it's a one-step separation process for decontaminating water. It's convenient and easy. It's very simple in design, and it applies to both inorganic and organic contaminants. It saves on energy and is versatile, especially for developing countries like South Africa. The adsorbents are often reusable, and it's very effective for removing low concentrations of contaminants in large volumes of water. We have made a number of nanocomposite adsorbents. For example, we have combined multi-walled carbon nanotubes with sugarcane bagasse. We have combined a waste plant material, Raphia foraminifera, with magnetite. We have doped multi-walled carbon nanotubes with cobalt ferrite nanoparticles, or we have taken the nanotubes and added silver nanoparticles to act as a disinfectant and combined it with waste biomass as well to remove contaminants. We have also made partially reduced graphene oxide and wrapped it with layered double hydroxide, which was extremely effective for reducing lead. And we have also functionalized the multi-walled carbon nanotubes with nitrogen donor ligands. So let me show you some of these materials that we have made. Well, why did we incorporate biomass? We've just heard a wonderful talk on plants and their effectiveness, but they can be used in many ways. Well, plants, as you know, are very abundant, they're renewable, they're low cost, they're environmentally friendly, and often we have a lot of byproducts from the agricultural industry or the sugar industry, such as here bagasse. This is the Raphia foraminifera, and this is Annona muricata petals that we have used in our work. So you can just go out and pick up this material, clean it up, and use it. This plant material contains cellulose, hemicellulose, and lignin. And if you look at the molecules, you see they're all functionalized. They have oxygen functional groups in particular that can be used to bind contaminants through hydrogen bonding, through electrostatic interactions, and even chelation. Now, this plant material is not sufficiently strong to be able to be reused over and over again. So it is useful to combine it with nanomaterials, such as I've shown here, a multi-walled carbon nanotube. But this is not functionalized, so it is best to oxidize it in acid in order to add oxygen-containing functional groups on the outer surface, which will help to interact with the biomass, but also with the contaminants and help in binding them. Now, I told you that we also took the functionalized nanotubes and added silver ions to it, reduced it with a plant extract to silver nanoparticles to embed disinfection properties into the composite. And then we enveloped it in waste biomass. We have also used magnetic materials such as magnetite, and here you see its cubic inverse spinel structure, in order to be able to remove the adsorbent after use through use of a magnet. The materials we made were tested by batch adsorption studies, where we investigated the effect of different variables such as pH, contact time, the initial pollutant concentration, the adsorbent dose, and temperature. This data was then fitted to isotherm and kinetics models in order to get the thermodynamic properties and the kinetics properties. But in addition, we performed desorption studies to see whether we could then remove the pollutants off the adsorbents and be able to reuse the adsorbents. So let me tell you about the first nanocomposite that we made between multi-walled carbon nanotubes. They're shown here. You can see their nice tubular structures. And then we added sugarcane bagasse, and you see the composite here. The nanotubes are all enveloped in the biomass material. This material was used to remove 6 different types of heavy metal ions, and as you see here, it worked best with the lead cation, and the least performer was the nickel cation. We did these studies both in single metal ion solution and with all 6 together, and you see, even though when there's competition, there's still good removal, but the behavior changes slightly, that over this region now chrome is better than lead, whereas in single metal ion solution, lead was by far much better than any of the other metal ions. If we look at the Langmuir monolayer adsorption capacities, then we see that it's very high for lead. It changes somewhat when we have all the 6 metal ions together, but it's still a good removal capacity. All the reactions were spontaneous. They were mostly endothermic and entropy driven, right? And the desorption percentages of the metal ions were good, apart from chromium, which is very difficult to remove. We then prepared the material where we had the silver nanoparticles that provided good disinfection properties, which I haven't shown here. But again, there we have the biomass, we have the composite, and again, the monolayer adsorption capacities were very good, especially for chrome-6, which you know is highly toxic. This material was also used to remove dyes such as rhodamine B and malachite green, and there again we had good removal efficiencies. So not just for heavy metal ions, but also for dyes, which are difficult to remove from water. We prepared a magnetic material where we combined raphia farinifera biomass, waste biomass, with magnetite. You see there the material is very homogeneous. You can see from the transmission electron microscope images the crystalline nature of the magnetite present in the material. So showing that both materials are combined in the nanocomposite. This again was tested on heavy metal ion removal. Not quite as good as when you have multi-walled carbon nanotubes, but again, a fairly good removal, and again, lead is removed best. And in this case, nickel is not the worst, copper was the worst. But this material has the advantage that, as shown in this image, you can remove it through magnetic means rather than filtering, which is often very difficult to do and time-consuming. We also took multi-walled carbon nanotubes and doped them with cobalt ferrite nanoparticles. And you see images here where you can clearly see the hollow nanotube with the cobalt ferrite nanoparticles on the outer surface. This was used to remove rhodamine B dye, and again, a fairly good Langmuir monolayer adsorption capacity was obtained, and again, the dye could be removed and the material be reused. We have then used a different material, namely reduced graphene oxide. We took graphite and produced graphene oxide by the modified Hummers method, and then we enveloped it in a magnesium aluminium layered double hydroxide. We varied the composition of the layered double hydroxide to be 0.1, 0.3, and 0.5 molar, and you see here the curves for lead removal, and we got good efficiencies for removing lead with this more complex nanomaterial. We then also tried to change the functional groups on our multi-walled carbon nanotubes. We prepared a nitrogen donor to a pyridine ligand, which we bound to the outer surface of the tube. And then we tested that material, and the material is shown here. It still maintains its tubular structure even when the ligand is bound to the outer surface, and it showed good removal of heavy metal ions, but also emerging contaminants such as bisphenol A and ibuprofen. Here you see the removal of heavy metal ions when they are in a combined solution together. So we have competition here. And again, you see that lead is best removed, and in this case, zinc was the least removed, but then we expected that because this is a nitrogen donor ligand and zinc prefers oxygen. So those were some examples of the adsorbents that we have tested and prepared for decontaminating water. But we have also looked at preparing photocatalysts, and we have based these photocatalysts on iron oxides because iron oxides are naturally abundant. Their synthesis is easy. They have a high surface area to volume ratios, particularly when they are nanoparticles. They exhibit superparamagnetism. They are not toxic. They're chemically inert. They're biocompatible, and they absorb visible light. Their only problem is that the electron-hole recombination sometimes is too fast, but this can be overcome by doping. We have based our photocatalyst on the perovskite structure, named after Count Lev Perovsky, a Russian mineralogist, and this family of materials has the same crystal structure as calcium titanate. It has the general formula ABX3, where A is typically a large rare earth metal ion and B is a smaller transition metal ion. So I'm going to show you one example here with this structure where we have the iron oxide with neodymium, bismuth and manganese, and then we varied X most of the nanoparticles are porous. They have this porous-like structure, and they're also crystalline, and the particle sizes were in the nano range, so these were nanomaterials. The strontium material had very good photoluminescence properties, which means it can be used for other uses as well. But the best catalyst was the one that incorporated calcium. Calcium had the best photocatalytic power for destroying rhodamine B dye, and you see here the starting material is very pink, and then the final solution after 2 hours of irradiation is clear. This was also exhibited when we did the chemical oxygen demand measurements, and you see again that calcium is the best performing of the materials and barium is the least performing. So in conclusion, we can say that nanomaterials with their unique physical and chemical properties have tremendous potential for contaminant removal, as I've tried to show you in this talk. However, we need to be wary because we are not yet completely certain of the health impacts of these materials and also their environmental fate. So we need to address these issues before we apply them widely. In finishing off, I'd like to acknowledge my colleagues that have been involved in this work with me, Professor Catherine Ngila, Professor Vincent Nyamori, and Professor Srikanth Jonalagada, whom you see here in these pictures, and our funders, the National Research Foundation of South Africa and the University of KwaZulu-Natal. And I'd also like to thank the various students that you see here who have been involved in this work. And last but not least, I'd like to thank all of you for your kind attention in this talk. Thank you.
Thank you very much, Professor Martin C., for this wonderful lecture, and especially for your time. I know we made you wake up early in the morning, and then thank you very much. And
Pleasure.
I think
Thank you.
We have time for questions. So if anybody has a question, yeah, I see a raise on hand. Okay, you can enable the microphone and go ahead. Am I audible?
No, I can't hear anything.
You're
Okay.
audible, but then
Yeah. Okay, I think it's
asking question. So.
okay. It's coming back. Okay, I see one raise on hand, so I thought of. I can't read the name. It's not in English. I think it's Hebrew, if I'm not wrong. Any questions?
Madam, thank you for the nice presentation. Ma'am, can you tell us something about the reusability of these composite materials? How many times can we use it for the adsorption of heavy metals?
They're effective for at least 3 uses, but we haven't tried further than that.
Okay, thank you, ma'am.
Do you hear me now?
Yes.
Yes.
Okay, so Professor Martisin, do you hear me?
Yes, I do.
This is Maurice.
Okay, hi. So
Maurice.
my name is Maurice Eisen. I'm a professor in chemistry in Israel. I was wondering, you show us the single metal and the multiple metal absorptions, and you show a difference between the absorptions when you have the single metal and then when you have the multiple one. Why you see that such a behavior?
I think there are synergistic and antagonistic effects that take place, but exactly what happens is difficult to ascertain. But there's obviously some are bind faster than others, and so the kinetics now is also involved.
Well, the kinetics will only change the rate, but then when you get the Landwehr,
they occupy the spaces, and once they're occupied, if they held tightly, more tightly than the other one, then the other one can't occupy the space, because remember, it's a surface effect.
But you did not measure K, the constant for the absorption.
We did. I just didn't show them here.
So the constant will be the one that will eventually give you who is going to be attached eventually, if you don't have diffusion problems.
Yeah, yes. I mean, we have the rate constants, but modeled, and then also the thermodynamics of the various adsorption, but for the singles, not for, it's much more complicated when you have them in competition and you don't have enough data points to be able to model it properly. I mean, you can see things, but they're not as, it's not as reliable because of the number of points.
Now, one more thing that I would like to ask you, if you can answer me, is that you show us the nanotubes with the sugar, for example, when you have this mixture of materials. But what happens if you don't have the nanotubes? So only the sugar, how that will work?
That works, but it's not as effective and it's not as durable. We did do those measurements where we took the nanotubes on their own and we took the bagasse on their own, but the adsorption capacities are not as high, and the sugar now is just finely ground leaves or the leftovers, the bagasse, and so it is not as durable for filtering and reuse.
Okay, thank you very much.
But it adsorbs less than the two combined.
Thank you very much for
Naveen.
joining in, Professor
Pleasure.
Morris.
Naveen, I have a question.
Yes, sir. Go ahead.
Okay. You talked about the functionalization of your nanotube, and then the nature of absorption is basically a chemical interaction with the functional group and the metal ions. You have the, for example, COH group and an OH group from that one. So the pH would play a major role into this one, because basically the uptake is by chelation, like you mentioned, chelation or in simple coordination. So if you want a coordination, you have to deprotonate, and then only it can happen. So probably if you try in the lower pH, a little lower than 7, higher pH, for example, little higher than 7, or perhaps 7.5 or 8, that means add alkali, and I'm sure actually your things would work much better.
We did investigate the pH because remember, you have to be very careful that you're not hydrolyzing the metal ion. So the first thing we do in these studies...
That's why I said you should not increase the pH high, 7.5 or 8, and that will not really hydrolyze the metal, and that one. A little bit of thing. And the important thing is you have to deprotonate the carboxyl group, then only the complexation would take place. And then you can have a better efficiency, but don't try to increase the pH very much.
Yes, no, most work best at around a pH of 5 to 6.
Yeah, if you increase a little bit, about 8, I'm sure actually your the nature of uptake will be very, very good, much better than what you find now, I feel. I mean, that's my suggestion.
No, thank you.
Oh, welcome.
I think we can take one more question. I saw some Dr.
Yeah, okay, one more.
Chakravarti.
If you don't mind, I have just one more.
Sir, I think we have one more question. So after that,
you
can go ahead.
Yeah, I have a small question. Martin did a very interesting talk. Can you comment on the cost?
Sir, your voice is not audible. It's a little bit kind of.
Can you comment on the cost effectiveness of your technique? The cost effectiveness.
Sorry, can you just repeat your question, because I can't hear you?
The cost effectiveness of the technique. The cost effectiveness. Is it cost effective?
It's very expensive.
Is it
very expensive? I mean, the cost.
Yeah.
Well, the biomass is free because we just collected waste material. The nanotubes are going down in price all the time because they are able to make them much more easily. The ferrites, you apart from the ones with the rare earths for the photocatalyst, but you impregnate them with not very much material. But you can also do it with things like hematite, magnetite, and those are cheap.
Right. Interesting. Yeah. Thank you.
Pleasure.
Professor Padmanabhan, you want to?
One more simple question. You said you introduce your magnetite, and that will not really make it absorb better than the other one. I think you are using magnetite because for the magnetic separation. But I noticed that most of your compound will be a solid material, and after absorption, actually the whole thing will settle down. Even without introducing the magnetite, you can have everything solid at the bottom, I feel. And you can
not really, because remember, some of them, even the magnetite is nanoparticulate, so it's suspended. Okay. So you want to be able to remove it, and filtering isn't, or it's very slow when you've got those small sizes.
Okay. Thank you.
Pleasure. Thank you.
Okay, we still have about 4 minutes for if anybody has any questions. I saw somebody posted, Dr. Neelanjana. Do you still want to ask a question, Doctor? Okay, so if we don't have any more questions, let's all thank Professor Martin C. for this wonderful talk, and then especially for her time. Thank you very much.
Pleasure, Dr. Kulkarni. Thank you so much for inviting me, and it's been a pleasure to be part of this wonderful conference. Thank you. And thank you to all the audience.
Thank you. Okay, now it's time to move to the our next speaker, Professor Sabu Thomas. I request Dr. Sarita to give a brief introduction about Professor Thomas.
Namshivaya, am I audible, Naveen?
Yes, ma'am. Yes, ma'am.
Okay. It is indeed my privilege to introduce the honorable speaker of the session, Dr. Sabu Thomas. Professor Sabu Thomas is a Vice Chancellor of Mahatma Gandhi University and the Director, School of Energy Materials. He is also the Founder, Director and Professor of the International and Inter-University Center for Nanoscience and Nanotechnology, Mahatma Gandhi University. Professor Thomas received his PhD from the Indian Institute of Technology, Kharagpur. He is an eminent researcher in the field of polymer science and nanotechnology and has more than 1,000 peer-reviewed research papers, reviews, and book chapters to his credit. He has also co-edited 107 books and has more than 50,000 citations. Professor Thomas has also received a number of national and international awards, which include Fellowship from the Royal Society of Chemistry, Distinguished Professorship from Joseph Stefan Institute, the MRSI Medal, Nanotech Medal, CRSI Medal, Distinguished Faculty Award, Dr. APJ Abdul Kalam Award for Scientific Excellence, the Lifetime Achievement Award of the Malaysian Polymer Group, Indian Nanobiologist Award, and the Sukumar Methi Award for the Best Polymer Researcher in the country. Very recently, Professor Thomas has been awarded Senior Fulbright Fellowship to visit 20 universities in the US. Recently, he was also awarded with the National Education Leadership Award for Excellence in Education. We are indeed honored to have Dr. Sabu Thomas with us today. Let me welcome Dr. Sabu Thomas to deliver his lecture on interfacial modification in nanocomposites to tailor functionalities.
Very good morning to all of you. Thanks, Dr. Sarita, for the kind words of introduction. And thanks to Dr. Kulkarni, Professor Padmanabhan for the invitation. It's a wonderful conference. Congratulations to Amrita for organizing such a good, marvelous international conference. The title of my presentation is Interfacial Modification in Nanocomposite with Tailored Functionalities.
Sir, sorry to interrupt. I think you have to put it in, yes. If you can put it in the slideshow mode. Now we don't see the slideshow mode.
Okay. Can you see my slide now?
Yes, sir, but now we see all the slides together and not as a slideshow.
Is it okay now?
No, you have to this slideshow. The right bottom you can see that one.
Yeah, mine is slideshow. I don't know what's the problem.
Yeah.
Mine is full slideshow.
Okay, but here it is actually showing us the editable version.
Yeah, I understood. How is it now?
Still the same. Naveen, can you take, you do you have the copy with you so that?
Yeah, I have. You see, I've sent my copy to.
Yes, sir. I'll try that then.
You
I'll
try
just
that because
open it.
my computer shows full screen.
Okay, sir. I'll do it.
Yeah, this happens sometimes. I don't know why. My computer shows full screen.
Just go ahead and share this. Window. Okay, I hope all of you can see the screen. Is it visible now? The slideshow?
Yes. It's okay.
Yes,
It's fine.
Okay, okay. Sir, you can instruct me to move the slides. So I can.
Can I start my presentation?
Yes, sir. Yes, sir.
Is it full screen now?
Yes, sir.
You are starting. So I will tell you. See, the title of my presentation is Interfacial Modification in Nanocomposites. What I'm going to show you is within 30 to 40 minutes, how the interface of polymer nanocomposites could be modified to meet the required applications. My presentation is, can you all hear me? Can you all hear me?
Yes, sir.
I will have a few slides, introductory slides. Then I will talk to you about clay polymer nanocomposites. And then we have applied these new findings to work with the entire company. So we made inner liners, inner tubes. Then I will talk to you some of our work on CNT, rubber nanocomposites. Then we had a project with the general cables where we applied mixed nano fillets in polymeric materials to make cables, cable compound. Then I will show you some of my activities with ISRO on super tough materials. We did some work on sensors, a couple of slides on thin films. Then I will come to biological nanomaterials, bio-nanocomposites. The previous speaker also talked about some of the interesting biomaterials, bio-nanocomposites, and for tissue engineering. Particularly, I will focus on tissue engineering. The former speaker spoke about water purification. And finally, a few concluding remarks. My research group is quite active on a variety of materials, graphene, CNTs. Next slide, please. Next slide. Yeah, my group works on a variety of material, graphene, CNTs, metal oxides, variety of nanomaterials. Next slide. Polymer nanocomposite play a very important role, for a large number of applications. When you put these materials into nanomaterials into polymers, you get lots of property improvements. And we can classify nanomaterials based on their aspect ratio. Aspect ratio 1, aspect ratio 10 to 20, or aspect ratio 100 to 200. When the aspect ratio is 1, the viscosity buildup is low. Viscosity buildup of the nanocomposites. But when you work with high aspect ratio fillets, the viscosity buildup is tremendous. So companies, they don't really like very high aspect ratio filler because the viscosity is so high. If you look at the reinforcement, you will find very interesting data. High aspect ratio fillets like carbon nanotube and graphene and clay, they give very exciting properties, especially mechanics. If you look at barrier is a very important property for packaging, automotive inner tubes, inner liners. There also you will find high aspect ratio fillets like graphene or clay is an excellent material. But if you look at dispersion, high aspect ratio fillets are very difficult to be dispersed. That's a very important issue because if you try to mix carbon nanotube in rubber, it's extremely difficult. They form lots of bundles, they agglomerate. Next slide, please. Next slide, please. Now I'm going to tell you the work with clay. You know, clay is a very interesting material. Clay has a TOT structure, 2 tetrahedral, fusion octahedral. And clay, the thickness of a clay platelet is very close to 1 nanometer. But clay has a very high stiffness. Very high stiffness. That is why the polymer people are really interested. But when you try to mix clay and polymer together, we have lots of issues, because if you don't do mix well, what will happen is the clay and polymer, they cannot interact. So you end up in a micro composite. If there is a very good mixing between clay and polymer, you get fully exfoliated system. And you can also see intercalated system. This is something intermediate. So if you do good chemistry on the surface of clay, on the surface of polymer, then you can have well exfoliated nanocomposites. Next slide, please. Can I see the next slide? Yeah, so my group is quite active in bridging polymer mineral interface. So there are different strategies to do that. Lowering of surface energy of the inorganic silicate, because the mineral surface is polar, and polymers like polypropylene, polyethylene, natural rubber, they are non-polar. So there is always a mismatch, a compatibility mismatch. So we have different protocols. We can use surfactants, we can use functionalization techniques, we can use block and graft copolymers. So one of the important ways is, you can use compatibilizing agents, surfactants. If you look at this slide, you can see we have tried different types of surfactants. Surfactants have a hydrophilic functionality and a hydrophobic functionality. The hydrophilic functionality will go to the clay surface, and hydrophobic functionality will go to the polymer surface. And then you make a strong interface. Next slide. Next slide, please. Go slowly. Next slide. So if you look at the compatibilizing agent, no, go back, go slowly. If you look at the compatibilizing agent, there are a variety of compatibilizing agents, amino acids, alkylamines, polyetheramine. There are a variety of surface active agents. Next slide, please. So if you look at the next slide, please. If you look at the surface active agents, what they do is they have a hydrophilic functionality that will go to the clay surface, and a hydrophobic functionality that will go to the polymer surface. Next slide, please. If you look at the schematic of this, you can see that when you treat the clay with a surfactant, the intergallery spacing is dramatically increased. You can see this slide. You can see that this is the close site as we received from a company, and the close site intergallery distance is very, very small, less than a nanometer. But if you treat with the different types of surfactants, you can see these are all treated clays. You can see that the peak is shifted to lower angle. This is a typical X-ray picture where you can see the neat clay, and you can see a series of clays treated with surfactants. And when you use a good surfactant, you can see that the peak is shifted to lower angles. What it implies? You increase the despacing. Once you have a good despacing, you can mix with the polymers very effectively, and you have excellent exfoliated system. If you look at this chart, you can see the surfactant just got a molecular weight 551.6. That is the best one. So my PhD students, what they do is they always treat clay with the different surfactants and find out the best surfactant. They find out which is the best one and which gives the best, highest despacing. I can show you one interesting slide. I had a, next slide, please. Next slide. I had a PhD student from France, an Indo-French program. Next slide, please. Yes. And what we have done is we have actually did some interesting polymerization. So she came with clay, and we actually polymerized clay and polyaniline. The next slide, you will see the interesting feature of our synthetic protocol. You can see the clay platelets, and the clay platelets have been transformed into nanocomposite by two techniques. One is we use clay with a surfactant. The surfactant is nothing but a diphenyl disonium cation. You can see this is clay, and in between the clay you have the disonium cation sitting inside. And then we went for oxidative polymerization of aniline. You know what we got? We got a completely exfoliated polyaniline nanocomposite. If you do a direct polymerization without treatment with disonium cation, that means without any interface modification, you know what we got? Intercalated polyaniline nanocomposite. And let us look at the property. If you look at the property of this material, conductivity is extremely high, 5 times higher than the intercalated system. And if you look at the stiffness of this, the stiffness is 4 times higher than the intercalated system. You see, a small chemistry can make wonders. My message is, when you manufacture polymer nanocomposites, you have to apply the suitable chemistry. Therefore, the polymer and nanofillets interact very strongly. Next slide, please. Next slide. I will show you some of our interesting work with Apollo tires. You know what we did is we did a quite interesting work with the tire company. You know, the automotive tires, we need to have inner liners or inner tubes. Once you pump in nitrogen or air, it should stay in the tire. So we had an interesting cooperation with the tire company. And the most important property here is the barrier properties. You have two cartoons here. On your left-hand side, you can see macrofillets filled with rubber. On your right-hand side, you can see organized clay platelets. They are uniformly organized. And you can see the right-hand side, when you fill the rubber with organized clay platelets, well-oriented, the incoming gas molecule takes a complicated diffusion pathway. If you put bigger particles like carbon black, you know, the air or nitrogen can diffuse quite rapidly. So we made impermeable membranes by brilliantly putting clay in natural rubber. Again, we have used different types of surfactants to exfoliate the clay platelets in the natural rubber matrix. Next slide, please. Next slide, please. I will show you the interesting data we got. Oh, please go back. You have to operate very slowly. Go back, please. Yes, look at this slide. The air permeability of neat rubber. If you look at the air permeability of neat rubber, natural rubber is highly permeable to air. So you cannot manufacture automotive inner tubes or inner liner with natural rubber alone. Look at the next, bar graph. If you use just 5% of bentonite or 5% of fluorohexeride with brilliant chemistry, natural rubber is transformed into an impermeable membrane. So we had a series of patents with the company. Next slide, please. Next slide. See how we have organized the nanomaterials in natural rubber. You can see the organization of clay in natural rubber. They were well oriented, well disposed, and this sort of orientation gave a very hindered pathway for the diffusing molecule. So natural rubber became extremely resistant to diffusion of air, diffusion of nitrogen. So the company is actually manufacturing tires using this technology. Next one, please. Next one, please. I will show you some interesting work we did with soft materials, soft rubber. Again, we have taken synthetic rubber, styrene butyrene rubber. It's a very important synthetic rubber for a large number of applications. And you can see my PhD student, Dr. Gigi Abraham, my collaborator, Dr. Sonny C. George. So what we did is we incorporated multi-volt carbon nanotube in SBR rubber. So we made soft elastomeric matrices for EMI shielding. Next slide, please. Next slide. Look at this slide. What we have done is, you see, multi-volt carbon nanotube cannot be easily disposed in SBR rubber. They always tend to